All right, so it's 12 p.m. Good morning once again, and welcome to Newtonian Mechanic class. My name is Festus, as usual, and I will be the facilitator. Yeah, can you hear me, please?
Okay, yes, please. Yes,
All
sir, you
right,
can. Good afternoon.
okay. Okay, so but before I start, the course, we need mathematics to understand the course. So we have to try and then revise our mathematics that we learn. Okay. So now when you talk about quantum mechanics, it's about on from modern physics. So there is no difference between modern physics and then quantum mechanics. But what quantum mechanics seeks to do is that it uses mathematical concept to explain the motion of what particles. Okay. So quantum mechanics basically is just a fundamental theory in physics that
Okay,
describes the behavior of matter and then energy and how
I hear you, sir.
you cannot hear me. Okay, let me see. Hello.
Yes, the network on
Okay.
your side.
Please kindly check your
We can
connections.
hear you well, sir. I believe we got.
Thank you. Thank you so much. Okay. So I said that before we will
Network.
start, and then if we want to appreciate this course, we need to revise our math because we need mathematics to be able to understand the subject very well. And I was saying that this is a continuation from our modern physics that we learned just the ended semester. So the only difference is that we are moving into details in quantum mechanics than the modern. The modern was just an introductory part of the quantum mechanics. Now, when you
Hello.
mention the word, hello, hello,
Hi, hi.
okay,
Yeah, you're there.
okay,
Please, I think it is better if you can mute all of us because I think it's background noise that is
all
coming
right.
in.
So let me see. Yeah. So please, when you join, make sure you mute yourself, okay, so that we can have a good background for the lecture. All right, so I'm going to start all over. So when you say quantum mechanics, what it seeks to do is that it is a fundamental theory in physics that describes the behavior of matter and energy at the smallest scales. So such as when you talk about the atoms, the subatomic particles. And this provides a framework for understanding the physical world, different from that. So it's different from the classical mechanics. So if you can recall from our modern physics that we learned, we said this concept or theory came up as a result of what certain concepts that could not be explained based on the classical point of view. So when you are describing a particle at the subatomic level, the classical knowledge that we know about physics ceases to fail, and that is where we talk about concepts like the particle dual nature of light. We talk about the Hansberg uncertainty principles. We talk about the de Broglie wavelengths. So all these things are the concept that brought about quantum mechanics. Okay, and this quantum mechanics began with the work of some physicists. That is, you talk about Planck, the Dirac, de Broglie, Herzberg, talk about the Bohr, Schrödinger, and then the rest. So in the quantum mechanics, we mostly use the Schrödinger equations. So that is the fundamental equation we use there, just as we use the Newton second law of equation in classical mechanics or in Newtonian mechanics. So this concept actually started in the early part of the 19th century. Okay, so that is the time the breakdown came up, that scientists begin to realize that no, they have to change their dynamic of thinking in physics about certain concept. Okay, so basically that is the history or the introduction of quantum mechanics. So we need to understand the history before we can build on. Because if you don't get a Faraday, there is no way that we can appreciate the course. And as I told you earlier, it is an abstract subject. The subject itself is abstract, and we need mathematics to be able to understand it. Okay, so if we take it from the history, then that will enable us to understand it better. So now these are our expectations at the end of the first unit. So we'll go to the sections. So the first section is the history of the quantum mechanics, and that is what I summarize. So I said this one started in the early part of the 19th century, 1900 to 1930. That is the duration. And how does it came to existence, or what happened? And then we have the quantum mechanics. It happened because certain concepts could not be explained based on the classical point of view. And those concepts are the particle dual nature, talk about the de Broglie wavelength, talk about the Hesberg uncertainty. Okay, so these are, and then photoelectric effects. So all these concepts brought about the birth of quantum mechanics. So within the section, what we are expected to know is we explain the history of quantum mechanics, and then explain black body radiations and solve simple problems. So I realized that when I teach by writing, we don't normally move faster. So we'll follow the model. Then if there is a need for us to write, if there's something that we need to solve, I will project the blackboard and then we'll all solve it together there. Okay. So the history, I will entry that you read on the history. So maybe where I will start is this flowchart. So now the flowchart here talks about the various aspects of physics. Okay, you see, within the classical mechanics, we have what we call the Lagrangian equation, which we will see then when we are doing the classical mechanics. Then you talk about analytic mechanics. Now, from the analytic mechanics, please, Mr. Bernard. Okay, thank you so much. Please be sure that you are muted. Okay. So when you look at the trend from classical mechanics, we are having Lagrangian equations. Okay. So within the classical mechanics, we only learn from physics 101, and then the rest we use only the Newtonian mechanics. But in the classical mechanics, we will add certain laws. So one of the laws or some of the discovery we'll be adding there is the Lagrangian and then Hamiltonian. So all these are within classicals. Then within the Lagrangian, we'll have what we call the analytical mechanics. Down from there, we'll have the Hesberg mechanics. So that is telling us that it is impossible for us to determine simultaneously, accurately, both momentum and then what position at the same time. So the accurate, the more accurate you are able to determine position, the less you will be able to talk about the position of the object. You know, every moving object has a momentum. Once it has a velocity, then it has a momentum, and then space, that is the position. Okay, so we move to the Lagrangian quantum path integral of Dirac Fermi. So all these things are also coming out from analytical mechanics. So if you are doing advanced physics, so you'll be meeting these concepts that I am mentioning. Then we have the geo-optics. So when you go to the geo-optics side, we have calculus of variation. Then we have the wave optics, whatever. So these are just like concepts that we have within physics. Okay, so you can, if you do advanced physics, you can try to specialize in any of these concepts that we are seeing here. So we see that everything come down to quantum mechanics and then Dirac formalism. Okay, so all the physics that we talk about is narrowed down to quantum mechanics. So it means that quantum mechanics supersedes all the physics courses that we've taken so far. Okay, so now we talk about black body. We said black body is an ideal body which is capable of what? Absorbing all incident radiations that are falling on it, regardless of the frequency or the wavelength, and then also the angle of incidence. So anybody that is able to emit or absorb all radiations that are falling on that body is what we term as what? The black body. And I think we saw this one in modern physics. Okay. So once it emits radiation, then you will get a spectrum. And we all know what we term as a spectrum. Spectrum is a collection of what? Various wavelengths of white light. So when you have a white light and then you're able to differentiate the various wavelength that is coming out from the white light, that is from the red to the violet. But you can do that by using a triangular prism. Okay. So now a black body is an object which absorbs from here, which absorbs, and then let me come. So a black body is an object which absorbs and emits the entire radiation incident on it. Okay, so you can remind yourself in case you've forgotten of what we said about it in the modern physics. You can take note of this definition. Now, it is difficult to realize a perfect black body. One way to imagine a black body is not to think of it as a body at all, but rather a cavity with a small hole as shown here. So what the statement is saying that black body is basically a cavity. You have a body. Oh, sorry. Yes, so this is depicting a black body. So we have a narrow hole on it. Now, when light goes through the narrow hole, then it's scattered inside. So it's going to be reflecting. So it tried to find the hole out. So by doing that, the body will be absorbing the radiations that are coming in. So this is basically a structure that is depicting a black body. Now the radiation can make it in through the hole, but after internal reflections, very unlikely to escape. So it will just be reflecting within the body. It can't find the hole out again, and hence it is absorbed. So once it's happened like that, we said the light is being absorbed by the body. Now, when the cavity reaches thermal equilibrium, the emitter radiation from the hole equals the absorbed radiations. Okay, so we have a thermal equilibrium. So thermal equilibrium means if the temperature is constant, the inner temperature and then the outer temperature is constant, then we said the body is at thermal equilibrium. So when that is done, it means that the radiations that are absorbed or emitted will be the same thing as the one that is what absorbed. So at thermal equilibrium, the absorbed radiation is the same as the emitted radiation. Okay. So this is not painting. Okay, so don't worry. I wanted to highlight it, but now suppose the walls of the black body are at a constant temperature. So now if the temperature is now constant, then at thermodynamic equilibrium, a balance between emission and absorption of radiation is reached. Now the spectrum obtained can be characterized by this energy. So the energy as a function of velocity and the frequency, and then what temperature. This is new. It's frequency, where the small deviation of this is the energy contribution by radiation per unit volume of the body or object in the interval V to V plus dV. Okay, so this would be the energy of the spectrum. Okay, and it is taken from the limit of V to V plus a small change because there's going to be an elapsed time. Okay, so from the thermodynamic agreement, so this energy is shown to depend only on temperature of the radiate of the cavity. Okay, so this is the curves. Now the energy that are radiated by the black body depends on the temperature. See, the energy increases with what? Increasing temperature. That is the peaks. The peaks of the energy is increasing with increasing temperature. If you look at the first temperature, which is 1000 Kelvin, now you see that the 1000 Kelvin has the lowest peak. So if you check with the energy axis, that will have the lowest energy. Then as the temperature increases, you see the energy is also increasing in terms of what the peaks. Okay, so with the 1400 temperature having the highest energy, but the energy is plotted against frequency. Okay, it's plotted against frequency. So you take note of the variables. So when you plot the energy against frequency and you begin to vary the temperature, then you realize that the energy is increasing with what? Increasing temperature.
Sir,
Yes, please.
so you said energy is plotted against, but what is here is intensity, voltage against intensity, or?
No, it's not voltage. The V is new. It's called new, which is frequency.
Okay. Then the E is?
And then it's energy. The energy of the photon. Or the spectrum, you can put it that way, yes. So, but the graph that we are seeing here, like there is a condition before you can achieve or obtain this graph. That is when it is in thermal equilibrium. Okay, so or when the system is what? In thermodynamics stable. Okay, so it means that aside that condition, it means you wouldn't get this peak. You wouldn't have the energy being increasing with increasing the temperature. Okay, so this is self-assessment that you will try to yourself. You give a summary of the origin of quantum mechanics, then briefly explain black body, then sketch a spectrum of black body radiation of energy as a function of this. So kindly try it at your leisure time. So if you are able to do it, in case you chance it in exams, you will be able to, do it. Okay, so the second session is we talk about equipartition theory and then specific heat of solid. Okay, so we learned heat capacity and specific heat capacity when we're dealing with introductory to atomic heat and objects here. So here we want to use the equipartition theory to actually come out with the formula for the heat capacity or the specific heat capacity. You know the definition of the two of them. Specific is talking about 1 kilogram mass of a substance, the energy you need to raise the temperature by 1 kilogram mass in 1 Kelvin. That is specific. But when you talk about heat capacity in general, it's just like how much energy you need to raise the temperature of the body. Okay. So here we will expect that at the end, we should be able to explain the principle of equipartition. Then we derive equation regarding the principle of that, and then also explain specific heat capacity of solids and solve simple problems. So let's now see the meaning of or the principle of equipartition. Now, the word is talking about partition. Partition means what? Division or divide. And then we're talking about equal. Equal means a divide into two. So now the equipartition theory states that energy is shared equally amongst all energetically accessible degrees of freedom of a system. So what it means is that when you have a system and the system happens to have maybe 1 degree, 2 degree, or 3 degree of systems, freedom, sorry, either 1 degree, 2 degree, or 3 degree of freedom. Now, how is the energy that you are giving to the system spread equally in all directions? So when you talk about degree of freedom, it talks about the XYZ plane. Okay, so if you are dealing with the XYZ, it means that you'll be talking about 3 degree of freedom. If you're talking about 1D, whether X, Y, or the Z plane, you talk about what? Just 1 degree of freedom. Okay, so you have a system, let's just say maybe a box that contains some balls or something of equal sizes. Now you happen to give energy to that system. So you expect the particles that are inside the box to move in these 3 dimensions with equal energy. So you know that definitely some should move maybe vertically, others should move horizontally, others should move diagonally. So if they are moving that, what is the energy in all the directions or the dimensions that they are moving? So you want the energy to be what? Equally distributed. So that is the principle of what? The equipartition. Now, this is not particularly surprising results and can be thought of another way of saying that a system will generally try to maximize its entropy. We talk about entropy is the hotness. No, that is how the system has been what destabilized. So like, how will I put it? So let's say you have a system at equilibrium, the particles within the systems are stable. Now, when you subject energy to that system, you realize that the particles within the systems are moving, they are moving around. So it means that you are increasing the entropy of that system. Okay, so how you are disorganizing the particle within the system is what we term as the entropy, and it is what? Energy. So, okay, that is how spread out the energy is in the system. Now, by distributing the available energy equally amongst all the accessible modes of motion, okay. So that is what the equipartition theory is saying. Now, to give a rather contrived example, consider a container in which we have placed a number of ping pong balls. So there are balls placed in the container here. Okay, so if you look at this figure, so A they move in the same direction. So if you can see from your end, you see that they are moving from left to right in the first box or solid figure there. Then, but when you come to the second box, you can see that they are moving randomly. Some are moving up, others down, diagonal, and in that order. So what the figures depict is that now this is exactly the same results as predicted by the equipartition theory. Now the energy is shared out evenly amongst the X, Y, and Z translational degrees of freedom. Okay. So the energy is moving in the 3 dimensions equally. Now the equipartition theory can go further than simply predicting that the available energy will be shared amongst the accessible modes equally, and can make quantitative predictions about how much energy will appear in each degree of freedom. Okay, so the degree of freedom that I just mentioned talks about the XYZ. So if it is the first X, just one. If it is 2 dimensions, that is XY, then you have 2 degrees of freedom. Then if it is XYZ, then you have 3 degrees of what? Freedom. So specifically, it says that each quadratic degree of freedom will, on average, possesses an energy this. So each degree of freedom. So each has to do with either X, Y, or Z. So in the Y direction, we have this average energy, which is half kT. Okay. So if it is like 2 dimension, it means that the 2 will cancel the 2, then it will be left with kT. If it is 3 degree of freedom, then it will be 3 out of 2 kT. Okay, so now let's see. There's a quadratic degree of freedom is 1, for which the energy depends on the square of some property. Consider the kinetic and potential energies associated with translational, rotational, and vibrational energy. So when you give the energy, or you subject the energy to the balls in the box, now there's possibility that some of them will undergo a translational motion, others will undergo vibrational motion, and then others will undergo a rotational motion. Now, translational is linear. So that linear motion, translational means a linear motion. So the kinetic energy for a linear motion is half mv squared, as we know. Then when you come to the rotational, because it will have an angular frequency, so we'll write our kinetic energy as half I omega squared. The omega is the angular frequency, and then the I will be moment, because it's going to be rotating. Then we have vibrational degree of freedom. So we have vibrational energy from elastic materials like a spring. So if you write the kinetic energy in terms of vibration, we'll get it as V is equals to the M is equals to K is equals to half mv squared, but the potential energy will be kx squared. So I think we will still see this one in classical mechanics when you are doing it. So you have the potential for vibrational system to be kx squared. Now, these 3 types of degrees of freedom all have a quadratic dependence. So the quadratic here talks about the square. So if you see the first one, V is square, omega is square, and then V here is square, X here is also square. So that is what we meant by quadratic dependence. So they all depend on velocity in terms of what? Square. On the velocity or angular velocity in the case of rotational, and therefore all follow the equipartition theory. So all these 3 equations that we are seeing here obey the equipartition theory. So one thing we should note is that when we are considering the vibrational system, we talk about harmonic oscillators. So the potential energy above here. So we talk about a particle that is being subjected or joined to a spring, and then you allow that particle to move within a boundary. So it is oscillating harmonically. So we know what a harmonic motion or oscillator is. Talk about a harmonic oscillator, it means that the acceleration is always directed towards the center. Okay. And the displacement is also opposite to the acceleration. So that is a harmonic oscillator or motion. Now, that is this. So another point about vibrations is that vibrational motion in molecules is highly quantized. And at room temperature, most molecules are in their ground vibrational state, and higher levels are not thermally accessible. So what this statement is saying is that when you come to the vibration, so most of the energy, they are in levels. Okay, they are in a discrete level, so they've been quantized or bounded. They have a boundary that they can move around, and they are always in the lowest level. So at equilibrium, you expect your system to relax. So when nothing is happening, you expect the system to be at its normal state or position. And once the energy are quantized and they have levels, so they can have level 1, level 2, level 3. So if you disturb the system, there is a possibility that the electrons or whatever you are dealing with can excite from the ground state level to any other state within the system. But when you withdraw that energy, from the system, you expect your particles to come down to the ground level. So that is what the statement is saying. So as a consequence, equipartition contributions from vibrational degrees of freedom near only usually be considered at a very high temperature. Okay, so we take consideration into higher temperature because we know that at a low temperature, there is no excitation. Okay, so the electrons are at their ground state or level. Now, conversely, at room temperature, please, low temperature is not the same thing as room temperature. When you talk about room temperature, you are talking about a temperature which is 300 Kelvin. Okay, that is a normal room temperature. So at room temperature, many rotational and translational states are occupied, and they can be treated classically. That is, as if their energy levels were not quantized to a very good approximation. So though we are dealing with quantum mechanics, but when you have your system be at room temperature, the system behaves as if the particles inside there are not quantized, and you can still treat it as what? A classical object. But once the temperature goes beyond the room temperature, you can't do that. Okay, so let's look at the simple derivation of the equipartition result for translational motion. Okay, so we can use the Maxwell-Boltzmann distribution of molecular speed to determine average kinetic energy of a particle in a gas and show that it agrees with the equipartition result. Okay, so we are trying to derive the equipartition result, and we do that using the Maxwell-Boltzmann distribution, and the distribution is expressed as equation 2.5. So the function, which is f, or the distribution function, which is a function of the frequency, is equals to 4 pi into bracket m over 2 pi kt all raised to the power 3 on 2 multiplied by the frequency square exponent this time. So m is mass, the k is the Boltzmann constant, T is absolute temperature, and then the nu, as usual, is our frequency. Now, when we average this, so the average kinetic energy, look at how we write average. So we use this bracket. So when you see anything in this bracket, it means that you're talking about average. So the average kinetic energy is written as this. So kinetic energy is equal to half mv squared. Then we put them in the average bracket to show that we are talking about the average. We want to find the 3 dimensions. So when you sum them together, then you get the average energy, because the principle says that the energy in all the dimensions might be what it could be same or equal. So you don't expect one direction particle to have energy more than that. So you have to try to quantify to get the average energy that the system will have. And that is equal to the integral of 0 to infinity half mv squared multiplied by the distribution function. So the average kinetic energy is defined as half integral of 0 to infinity half mv squared multiplied by the distribution function. So now, if we substitute equation number 2.5 into 2.6, we put 2.5 into 2.6, and then we factorize the constant term out. When you are doing integration, so anything that is not a dependent variable is treated as what? A constant. So if you look at it, we are taking it as the new. So any term which is not new should be taken outside the integral sign. So we factorize m 4 pi m over 2 pi kt all raised to the power 3 on 2 out, because we are treating them as what? Constant. Now here we have the new. New is not constant. You can't take it out because your dv here is the new. So that is why you are integrating respect to. Then with the exponent term, you have new there. So you can't take anything out here. Yes.
Okay, sir, please. He said you are factorizing the constant out.
Okay.
So there wasn't pi in the original question. So I don't know how pi was factorized out.
Check equation 2.5. The distribution function is 4 pi open bracket m over 2 pi kt all raised to the power 3 on 2. So we just take that term. You know what I've mentioned, there is no frequency term in them. So you can pick that one outside or out from the integral sign.
And sir, please, the exponent, it is it a particular value to the exponent or exponent what? Because
3 on 2.
Is that what?
3 divided 3 over 2. It's
No,
raised to
you
the
said
power.
when you have written after the v squared exponent to the power minus m v squared over 2 kt.
Okay.
And I said that particular exponent, is it the English exponent or there's a term that we are finding it exponent?
No, it's the expression in mathematics exponent something. So when you write a number e to the power 1, e to the power 0, so that is that exponent. Exponential is the English word that you know. When you talk about exponent, is a power, right?
Yes.
Yes. So this one is it's a mathematical expression. So when you take e to the power 0, so that means that the answer is 1. And e raised to the power 0 is 1. And any number raised to the power 0 is what? 1. And so now this is like when you write sine or cos. See, this is, we can call this one as an argument. So argument means it can't stand alone. You can't separate them. So if you write like cos omega t, you can't write omega and t separately. So that is an argument. So this is also an expression which contains these terms here, minus mv squared over 2kt. So it is a one term. You can take it as one term. Okay. So that is how it is. So back to the equation 2.7. So you see that 4 pi open bracket, whatever that is here before the integral sign, we don't have frequency term. So it is a constant term, you take it out. But when you come inside the integral sign, because we are integrating in respect to frequency, so any term that has frequency should remain inside the integral. So back to your exponent, you see that with the exponent, as I explained, it's a single expression or term, and it contains mass and then frequency. You can't pick the mass, the 2 and the kt out from the exponent. You can't do that because it is a one argument. Okay. So now this is a special function. Look at the expression of equation 2.7. What is inside the integral is a special function, and you can't integrate this to arrive at an answer without applying the Gaussian special functions. So I think, yeah, let me write for you to see how it came about. So let me share the other, and I'll show you. Can you see the PowerPoint at your end?
Yes, please.
Okay. So what we have is like this. I'm not on the lesson, but if you can mention it to me to write. So we have okay, so we are saying that the energy is expressed as, let me go back to, so I can write the exact expression there and then. Okay, so that's equation 2.7. So we are saying that the average kinetic energy is equals to 4 pi. Then we have mass on 2 pi kt. Then everything raised to the power 3 on 2. Then this is multiplied by the integral 0 to infinity. Then we have nu to the power 4. Then we have our exponent. Then we have minus m. Then nu square. Everything divided by 2 kt. And we are integrating respect to the frequency. Now, this is what we need to simplify. And I'm saying that you can't do this. This is a special function or expression. So if you can take the whole day to integrate it, but you will not get anything. You will not even finish it because it is very long and you can do. So you have to apply a Gaussian. So when you apply quotient integral or special function, we have this. So what the function is saying that when you take an integral of 0 to infinity of a certain expression to the power n, then e to the power a x square dx, then it is written as this: half a, then raise the power n plus 1 on 2, then gamma of n plus 1 over 2. This is gamma. Okay, it's not a square root, it's gamma. It is written as this. I will call it gamma, this word. Okay, it's G-A-M-M-A, gamma. Okay, so now this is a special function. We'll now compare the special function to our problem. Then we try to now simplify it. So if we look at it, the exponent here is the same e here, so don't be confused. You can write it this just like this, or you write it in a short form. It's like this: exponent something. Okay, so by comparison, you realize that here I have v and I have exponent with a certain term. Then I'm integrating respect to what? V. The same way here I have x, which raise the power a certain number, and have the exponent term, and then I'm integrating respect to the x. So you see that this your problem here resembles the special function. So I can go ahead and then treat this one as my special function. Is that okay? Did you understand what I'm saying? Hello, is somebody there?
Yeah, I think we should go over again.
Okay. So the essence of what I'm doing is that we cannot explicitly, integrate this. We can't do that. So we need to invoke the integral of special functions. And it is saying that when you have any integral in this form, so if your integral is like this, then you simplify it as this. Simplify it as this. Okay. So if you look at our problem, what we want to integrate.
So please simplify it as I didn't see the cursor, please.
That is what I've written, equals to half a raised to the power.
Negative.
So whatever that is at the left hand side is the same thing as the right hand side. So instead of you picking this to integrate, you will forget about this and then pick the right hand side and substitute your values. That's the meaning. Are you following? So in other words, the left hand side can be written as the right hand side. And I'm now saying that if you compare what we want to integrate to the expression of the special function, you realize that look at the integration limit. It's taken from 0 to infinity. Ours is also from 0 to infinity. We have a certain variable, which is v. We have v, but we define it as x. And that variable is raised to the power a number. The n stands for any number at all, any value. So 1, 2, 3 is an integer. So it means that our n here is 4. So by comparison, then we have the exponent e. We also have our exponent. Now our exponent is raised to the power a x squared. Look at it this way. So by comparison, we can say our a is m over 2kt, because if you take this one out, m over 2kt will be left what? Nu square, which is also what? X square here. Is that okay? And it is being integrated respect to the first letter, which is x here. And this one too is integrated respect to the first letter, which is v. So it means our function here is a special function, which we need to treat it as the right hand side. I hope we understand.
Yes, sir.
Okay.
Yes, sir.
All right. So it means by comparison, we can say that n is 4, and then so we will now write our integral as this. So let's say my kinetic energy average is equals to 4 pi. Then I'll have m over 2 kt, m over 2 kt raised to the power 3 on 2. Then I multiply by I, where my I is defined as integral of 0 to infinity. Then I'll have v to the power 4. I'll have exponent minus m nu square over 2 kt. Everything raised to the power of what? No, nothing. So I'll now have dv. Okay, but this same thing is expressed as this. Half, then I'll have a to the power minus n plus 1 on 2. Then gamma of here, gamma of n plus 1 on 2. So gamma of
So my half
n plus 1 on 2. Okay, so by comparison with the formula that I showed you here, the special formula, let me come back here. So by comparison, you can see that n is 4. So let me start from the x. X is the same thing as v. So n is 4. Exponent is the same thing as exponent. When we come, we have minus. We have our minus inside here. So our a here is m over 2 kt. You can see that. Then our x square is our new square. Can we see that?
yes, sir.
All right, so let's go and then do our substitution there. Okay, so now, since we know that n is equals to 4, so we are solving for our I. So I will now be equals to this part, because it's equals to this. So forget about this one, forget about this. So we are now coming to use it. So I will now be equals to half, then a, then raise the power minus, our n we said is 4. 4 plus 1, all divided by 2. Okay, then gamma, we have 4 plus 1, all divided by 2. And in that case, this one will be simplified as what? Half a. Okay, let me make substitution for my a. Then we say a is what? M over 2 kt. I'm sure nobody is confused with what I'm doing from here.
Yes, but then say please, the a is to the power negative n plus 1.
Negative
N plus 1.
Yes.
But
Yeah.
we seem to have divided it
I
by
didn't
2.
write. I didn't write it.
We seem to have divided it by 2.
Here.
The power of a.
The power
No.
of a. Yes, the power of a is n minus n plus 1 on 2, which is here. Which is here.
Oh, okay. The
You see?
original one that you wrote was without the division by 2. That's why I was a bit confused.
Oh, it's cleaned. It's cleaned. There is. Oh, sorry,
So,
here. You see, the division sign is there. It means it clean automatically.
okay, all right.
Is there? Okay, sorry, thank you. So now I will substitute my a here. Now 4 plus 1 is what? 5 divided by 2. So this will be raised to the power minus 5 on 2. Then I have my gamma. So gamma, then 5 on 2. Okay. Now you can still simplify the gamma. The gamma is a factorial. So if you have gamma of something, let's say gamma of n is the same thing as n minus 1, open bracket, gamma, let me say gamma n minus 1. Okay, that is what. So, or if you have gamma n plus 1, is the same thing as n minus 1, and then gamma n plus 1. So you have that. So it's a way of reducing your expression. So you reduce the gamma expression to the smallest or to the least, so you can break it down. Let me show you this. I know if they've given you 8 factorial, you know what 8 factorial mean.
Yes, please.
So 8 factorial means you break the a to what its lowest. So that was going to be 8 times
7
times 7 times 6 times 5 up to what 1. And so in the same way, when we also have the gamma, you express it in that manner to the lowest. So the 5 gamma of 5 on 2 is not the lowest, so you can still move further to get the lowest value, which will be this thing, half. So you keep on reducing until you get half. Now, when you also get that half is also this thing, an identity. Okay, so it's an identity which is also root of what? Pi. So this is how you define the gamma. So if you have gamma p plus 1, it's the same thing as p gamma p. So the p stands for any number. P is an integer. An integer. So when you have gamma of any number, so let's say we have gamma of 5. Let's say if p is equals to 5. So it means that you can say gamma of 5 plus 1 will be equals to, the p is what? 5. So this will be 5, open bracket 5. Then you reduce this one by taking the factorial in that order. So simply you can just say gamma of n plus 1 is nothing but what? N factorial. So just as you know the factorial, you reduce it until it is the lowest. Okay, and then gamma of n is equals to n minus 1 times gamma of n minus 1. So we are having this. This is our problem. This is what we have. So we're going to use this expression because we have gamma of what? 5 on 2. When you come to our question here, here is 5 on 2. It's not plus something. So we will apply this identity to break that 5 on 2 down. So when we do that, so our gamma of 5 on 2, let's apply the same thing. So it's going to be 5 on 2 minus 1 multiplied by gamma of 5 on 2 minus 1. So we'll simplify. This is going to be 5 minus 2 on 2 multiplied by 5 minus 2 on 2, and that is in gamma. So this will give us 3 on 2, right? Then gamma 3 on 2.
Please, the
Yes.
marker is not clear. The marker is not clear.
All right, let me change it. Thank you. So let me use the white marker for you. Okay, but what I'm saying is that you will need to express the gamma into its lowest, just as we saw in the factorial. So I said, use an example as if you are given like 8, let me use something small so that we'll not waste time on it. So assuming you have 4 factorial, this is the same thing as 4 times 3 times 2 up to 1. then you get your answer. So the same way, when we have our gamma of n, we have to keep on breaking the number in the gamma until we get gamma of half. That is if it is a fraction. This is an identity. The moment you get to gamma of half, it's like you reach 1, and that will be root of what? Pi. Okay, so we have to keep on breaking the 5 on 2 until if you can get a gamma of half, then we terminate it. So we are using the expression on the box. So my gamma of 5 on 2 is 5 on 2. Using the formula, so it means n is 5 on 2. So I have 5 on 2 minus 1. Then gamma 5 on 2 minus 1. So this is still inside the gamma. Then 5 on 2 minus 1 will give us 3 on 2. So you are not going to do anything to this. Okay, but your focus should still be on the gamma because you wouldn't have 3 on a half. So this would be 3 on 2. Now you further break the 3 on 2 using the same formula. So this is also is equals to 3 on 2 outside times n minus 1. So the same 3 on 2 minus 1. Then again, gamma 3 on 2 minus 1. Oh, why this thing is cleaning itself. Okay, so this is multiplying. Now 3 on 2 minus 1, you multiply, there will be 3 minus 2 will be 1. 1 divided by 2 is half. So in that case, your expression will now going to be 3 on 2 times half. Then the gamma, what is inside the gamma will also be half. So half gamma. And I'm saying that this is equals to root of pi. So it means that we are now going to have our expression this. The gamma 5 on 2 is now going to be 3 on 2 times 1 on 2 times root of pi, because we know that gamma of half is equals to root pi. Okay, so we simplify. So 3 times 1 is 3, and then 2 times 2 is 4. So this will give us, so in short, gamma of 5 on 2 is nothing but 3 root pi on 4. So we'll now multiply this by what we have here. Let me come back to our expression here. So we have this one.
Before you continue, sorry.
Okay. No
where
problem.
we go to, please, if you could take us back to the previous slide. We have 3. So this time, this is the root sign for the one that
Yes.
is pi. It's no more the gamma, so it's 3 root pi.
No, yes. The last one, the
This
half.
one.
So it's root, no more gamma. So it changes to root. This is a square root.
All right. Then secondly, say, I wanted to ask, is the gamma
Okay.
a function on the calculator? Like, so
No,
it's not.
You can't see it there. So we have these special functions. We have what we call gamma and then beta functions. Okay. And they are very useful because they help us to solve a complex integral in an easier way and then simplest form. Okay. Okay. For the sake of knowledge, let me write a definition for you. At least we are learning. You don't know where we'll meet it again. Now, what I just talked about, I talked about beta. Okay, don't worry. Let's finish this. I will write that one for you. So now we have this. So let's go back to our kinetic energy. This is the kinetic energy. The average kinetic energy is expressed as this. So we are having 4 pi. Let me go back. 4 pi m on 2 pi kt. Okay, raise the power 3 on 2. Now, what we're having here as gamma, where is it? Here. So this is what, oh, Okay, so this is I. No, let me finish with I before so that you wouldn't be confused. So let me just finish with I before we now come to substitute. So you hold on with this one for now. Let me write it, complete the integral because I substituted for I. So our capital I will now express as this. So we come back to this side. So where is capital I? Capital I is half m over that. So this will give us half m over 2kt. Is it raised to the power? No. Or is raised to the power something? Yeah. So 2kt raised to the power minus 5 on 2. Minus 5 on 2. Then we'll have, let's come back here.
The gamma of 5 on 2.
So we now have gamma of 5 on 2, and our gamma of 5 on 2 is what we found to be 3 on 4 root pi. Okay. So now this is our integral. What we have here is what we were seeing here, v squared, more v to the power 4. We have the exponent to bracket minus m v squared over 2 pi kt. So that is what we now have it as I. So we'll go and substitute this I expression to our average kinetic energy. So let's now go and do that. So in that case, our average kinetic energy will now be expressed as this. Ke average will now be equals to, we have 4 pi and we have m over 2 pi kt raised to the power 3 on 2. Now we substitute the value or the expression that we got for the integral because we're having a multiply by I here. Where did I write that? Here. Yes, so here. It's here. So we now put our I value in this equation. Okay, so let's write our I. Now our I is expressed as this half times half. Then we have is it minus? Yeah, m. That's a m over 2kt. So m over 2kt, then followed by to the power minus 5 on 2. Raise the power minus 5 on 2. Then multiply by 3 on 4 root of pi. Okay, so we now need to simplify this. If you simplify everything, we'll get this one to be k on that would be half on kt. So that would be half on kt. The average in the kinetic energy will be half kt. Now, when you talk about the degree, which will now give us either 3 on 2 kt or just a kt. So when you talk about the kt, it means we are talking about what? 2 degree of freedom. So you can actually do that. And how do we simplify this? Just use your indices, okay? So if you look at what is here, this is pi. Let me write that one alone. 4 pi is here. So this one means that all the numbers inside this bracket are raised to the power 3 on 2, right? So it means that I can take this pi out. I can write this one as m over 2 kt, everything raised to the power 3 on 2. Then I'll write my pi. So multiply by this pi here. But pi was divided, so it has to be negative. So minus 3 on 2. Okay. Then times my half, this half. Then this is m on 2 kt raised to the power minus 5 on 2. Then I also have times 3 on 4 root of pi. So let me write the pi in terms of index. So root pi is half. So 4 root pi. So pi will be 1 on 2. So we apply indices. So in indices, when the bases are the same, we add the exponent. So when you do that, it will cancel out and you are left with kt, half kt. Okay. So already this 4 we take away the 4 down here. Now we have pi here. So pi to the power 1, and then we have pi to the power minus 3 on 2. Then we have pi half. Okay. So when you do it, this one will be half. This one will be minus 2. Look at it here. Let's add this one together. So this plus 3 plus 1 is minus 2. So minus 2 divided by 2 is what? Positive. It's minus 1. Are we following?
Yes, please.
And then 1 minus 1 will be 0. So this will be pi raised to the power 0. But any number raised to the power 0 is what? 1. So it means that the pi will go away. We will no more have pi. So pi will go out. Okay. Then you also pick the m on that. So we have m on 2 kt. Then it's raised to the power 3 on 2 plus, or no, minus 5 on 2. Minus 5 on 2. Okay. So if you also do that, this will give us, so this will be minus 2 on 2, right? Is that okay?
Yes. Yes.
So this will cancel each other. We are getting minus 1. So it means this will write as a numerator, a denominator, sorry, because you will now be m over 2 kt raised to the power minus 1. So if I take the reciprocal, this one can be written as what? 2 kt
on m.
On m. Good. So we can write this one as that. So it means that these terms here combine to give us this. Okay. But we have half. We still have half here. There is half here.
So I think that half will take care of the 2.
So half will take care of this. But I think we missed one of the step of the m. I think the m was dividing also. Okay, so this will take away. Let's look at our original equation.
Okay.
The original equation is what? 4, we have 2 pi, and then this 2k. I'm writing the correct one. So when you come to about 4 pi m over 2 pi kt, okay, then times our final expression we've got. I think we have kt on m, but we couldn't write that one here. Let's see here. The final expression that we've got for that. Our a, where's our a? A is this. Yeah. So you see the a was raised to the power negative 5 on 2. So when we take the reciprocal, it should be 2 kt on m. I think we didn't reflect that. That's why we are still having the m10. So in that case, the m would have canceled out. But that is how it's going to be. So this would have gone. We have written it in plenty. That's why we are not seeing it. Okay. So, and we have 3 on 2. You know that we still have 3 here. This 3. This 3 is here. Because 3, 3 on 4, then the 4 cancel the 4. Where is the other 2? There's a 2 somewhere. So this will cancel this 2. Then this should be 8. Okay, don't worry about that. If you can sit down and then do it yourself, but that is how you would do it. So in your manual, you see that the final expression of the average energy is this. So the average energy, kinetic energy, is expressed as 3 on 2 kT. And I'm saying that it's a normal kinetic energy. So the average is just half. So this is equals to half kT. But this 3 is telling us the degree. So the 3 here talks about the degree of the freedom. Degree of freedom. Okay. So when you are dealing with three dimensions, so this should be your average kinetic energy. But if it is just one dimension, maybe X direction or Y direction, so it is going to be half kT. But if we are talking about 2 dimensions, so 2D will be 2 out of 2, then kT. So this will cancel this. So 2 dimension will just be left with the kT. Okay. So that is what we've seen in our model.
That means 3 dimension will be 5 on 2 kT.
No, please. 3 dimension is what we've got. 3 on 2. It's like this. This is how it is written. 1 on 2 average, half of the kinetic energy. So average, this is kinetic energy. KT is kinetic energy. So average of it is half. Now, any factor you multiply by the half tells you the degree of freedom you are talking about. So if I'm dealing with 1 degree of freedom, I'll multiply by 1, which is still half. If I'm dealing with 2, I'll multiply by 2. So 2 will cancel. And I will be there over kT. So this one will be the average kinetic energy for 2 dimensions or 2 degree of freedom. Then if I'm dealing with 3, I'll multiply this one by 3. So which will give us what? The 3 on 2.
All right.
And so that is.
Okay, so please, the from the very beginning where we got the V to the power 4, I was trying to figure out how we got the V to the power 4.
Okay.
Do I understand this process at the very beginning?
Let me go back. You see, we're having our integral as this. We said 4 pi m on 2 pi kT. Everything raised to the power 3 on 2. Integral of 0 to infinity. Then we have v to the power 4, and we have the exponent, which is minus mv squared over 2 kT. And everything is being integrated respect to nu. So I'm saying that you can't pick this and integrate. It is very difficult.
Hello, sir.
Yes.
So this part I understand, but then transitioning from the half mv squared
Yes.
of f of v.
F of the very beginning.
The very beginning, yes.
So the very beginning says that the distribution function, which is a function of the frequency nu, is expressed as 4 pi of this. So it's expressed as this. Okay. The beginning, we first of all talk about the average kinetic energy, which we say is that the average kinetic energy is, so let me first define this and we'll come to that. So this one is equals to 4 pi m over 2 pi kT raised to the power 3 on 2. So let me put this one here. So let me just write it. This is what this. And this is the Maxwell distribution function. This expression is the Maxwell distribution function. But the average kinetic energy in terms of the degree of freedom is expressed as K with the bracket is equals to half then mv squared now multiplied by f of v. Okay, and this is taken from the integral of 0 to infinity. So this is the definition of the average kinetic energy. So it means that we need to substitute the expression of V of F of V, but already is defined in this as this.
Okay.
So when we substitute this equation into maybe equation star star, then because of the exponent term and this term, we can't solve it analytically to arrive at an answer. We need to use the special functions. And that is why we now define our special function as this to this. We have a certain variable raised to the power n with exponent of a certain constant times this. You look at these numbers, raised to the power 2, then the x. That one will give us half a the power n plus 1 on 2, then gamma of n plus 1 on 2.
So actually, sir, sorry, my only confusion was actually how, from mv squared, the v squared, now we now had v to the power 4. It's not about the special integral, but then how the v squared became v to the power 4 before we even brought in the Gaussian integral.
I've seen what you're saying. No, then it's yeah, it is. Okay, I've seen it. It's here. You see, from here. Now here is square. Here is square. Because I was writing the full thing, that's what I prefer. Here is square, is that not it? From the F, the definition of the F.
Yes.
Is square. Now, you see, you have the kinetic energy expression. You have V squared there. So you have kinetic energy is equals to half mv squared. So this V squared multiplied by the V squared term here, that makes it to the power 4. Are you following?
Okay.
From the F, the distribution function, we have V squared. Then in the kinetic energy expression too, we have V squared, and they are being multiplied. So when you are substituting, come look at this equation. So when you are substituting, you substitute half mv squared multiplied by whatever term you have here, and you see that there is another v squared here. So that makes it v squared. So v to the power 4. So v squared plus v squared will give us the v to the power 4. So this v squared plus another v squared times another v squared. So the bases are same. We add the powers. So this will be v to the power 4. That's how it comes about.
All right, sir. Thank you.
Then if that is the case, it means that the average kinetic energy here is supposed to be v squared, like the one you've done, which you have made it v to the power 4, not v squared, right?
Which one?
The kinetic energy you have written there before you brought in the special integral. It's supposed to be
this
the
one.
integral. The v is supposed to be to the power 4, right?
No.
Yes, since you said
no. You see,
let the v
from
there is
classical
special if you want to
mechanics,
simplify.
You see, from classical mechanics, how do we define kinetic energy? Kinetic energy is equals to what? Half mv squared.
Okay.
Is that not it? And then
yes,
the function is also having v squared. So 4 pi m over 2 pi kt to the power 3 on 2, then v squared, then the exponent term. You understand? So if you are multiplying, we are now coming to multiply the term here. So we are going to write it like this: half m v squared times 4 pi whatever you have. So we see that you come and have another v term here, which is squared, then the exponent term. So this v square with this v square will give us the v to the power 4.
Okay, so sorry. So then it means that before the exponent, there is a v squared.
Yes, from the distribution function. If you go back to the distribution function, there is.
That's why.
Okay. There is v square in both expression, the distribution function and the kinetic energy expression.
Okay.
Yes.
Okay, sure. So
Yes.
somewhere at the end of this unit, they said that you should define energy in terms of quantum mechanics or according to quantum mechanics. So it means that that formula goes by we go by kinetic energy is equal to half mv squared times
No, 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 no,
fv.
no, no, no. Once you talk about quantum mechanics, you should come in with a Planck constant and then a frequency. So that's why you're going to have this HFC, or which is HC on lambda. You can write it this way. This is the energy in terms of quantum mechanics, the energy of the photon. Or you can write it this way. This is equals to this. Any of this is correct.
Okay, thank you.
This omega. This omega. So these are the expression of energies in terms of quantum mechanics. But what we've gone through is the equipartition principle or theory, and which we learned that it stated that the energy that you subject to a system has to be what distributes equally along all the direction that the particles will be moving. Okay. So what the equipartition theory is saying that every object has 3 degrees of freedom in movement, and which is true. When you have a body at equilibrium and you subject a force to it, now classical mechanics will tell you that the body must move in the direction of the applied force. And so you expect the body to move in one dimension. But this one, we are talking about translation. You understand? So translation, it can rotate, it can do anything. So it can move in any direction. And you are not also dealing with one particular thing. There are so many particles that are responding to the energy that you subjected to. So some can move in the Y direction, others can move in the X direction, others can move in the Z direction. But you inputted a common energy. So you expect your total energy to be the sum of the energies that the particles are moving in their various or their respective dimensions or directions. So that is what we are saying, the average. So if I'm giving 6 volts or 6 joules of energy, then I expect element or particles that are moving in the X to have 2, Z to have 2, and then Y to also have 2. So when I add them together, I should get back my total energy. And so in other words, your total kinetic and the average kinetic energy is going to be 6 on 2, and that will give you your 3. And then this 3 will mean that you have 1 moving in X direction, you have energy 1 moving the Y direction. So when you add them together, you come back to the 3. So that is the meaning. Okay, so let me go back to our model. Okay, so at the end of it all, you see that our equation 2.10 is our average kinetic energy, okay, in 3 dimensions or degree of freedom. So when you come, so the average translational kinetic energy of a particle in a gas is therefore this, or half kT per translational degree of freedom. So depending on the translational degree of freedom, you can write it in 3 different forms. So one is 3 out of 2 kT, which is 3 degree of freedom, half kT, which is 1 degree of freedom, and then kT, which will be what? 2 degree of freedom. And in agreement with the equipartition theory. So that is what the equipartition seeks to explain. Okay, so any question before we move to the specific heat of solids? All right. So now the classical mechanics should be used with what? Caution. when dealing with phenomena that are inherently quantized. So quantization means they are bounded or limited. Okay, so you restrict their movement. Okay, so when you restrict their movement to particular dimensions, so then it will be different from when you are looking at it holistically. Now, due to thermal agitations, atoms in solid oscillate about their mean position. Okay. Now, when each atom is considered as three-dimensional harmonic oscillator, then its average thermal energy should be 3 kT. Do you understand? So the first one we talk about average, but this one will now be the total energy. Okay, so when you take out the half, so if you take half plus half, give us 1. So the full energy will be what? 3 kT. Or which is what? kBT is that of one dimension harmonic or dimensional harmonic. Okay. Oscillator. Then the thermal energy of a solid becomes 3 kBT. The kB is the Boltzmann constant. Then the T, as usual, we know is the absolute temperature per atom or this. So you have this per an atom. That's just a single atom. But if there are many atoms or electrons or whatever you are dealing with, then you need to add the Avogadro number or constant to it. Now we can write it as 3RT, and R is the molar gas constant, then which is the same as 3 NKBT, and N here is the Avogadro number. Okay, so that is how we express it. Now the 3R is expressed as this, so the R is 8.3 times 10 to the power 3 joule per what is mole, but they are using a kilomole, okay, because of the times 3. So the K here takes in the times 3. So kilomole then per Kelvin. Then the universal constant or gas constant, that's what we normally say for the R. And this was confirmed experimentally in solids at normal temperature, but for sufficiently low temperature, the specific heat decreases and approaches to 0. Okay, so when you are dealing with a system that has a lower temperature, that is when the temperature is approaching 0, then you have the specific heat capacity being what? Decreases, or also decrease with decreasing temperature. Now, in order to explain this, no, actually, in order to explain this, I think there's a typing error. In order to explain this, Einstein assumed that the energy of an atom is a solid. In a solid, takes only a discrete set of values. So what he did is that he looks at the energy as integral multiples instead of being continuous. We know continuous energy means that the energy is flowing constantly or continuously. But if you make it like causal, so it flow like it has a discrete, there are certain time it flows, certain time there is no energy. And so he wants to check it from that, perspective. So he had the formula as this, and that is the energy of the photon, that is h nu. This is frequency, so don't confuse the symbol with velocity. It's not velocity, it's frequency nu. Okay, so now Einstein assumed that the energy of an atom in a solid takes only a discrete set of values. So discrete set mean 1, 2, 3, 4, not like 1 point something, 2 point something, no decimals. Now the energy of each component of oscillations is NHF. So where n is what? An integer. So when you're talking about 0, n or electron, it means that once there is no electron, there is no energy. So when there are 2, what is the energy? When there are 3, in that order. So the mean energy per atom is obtained as this. So when he considered the energy as discrete, he came out with the average energy of the atom to be h nu over the exponential of h nu over kBt minus 1. So this is the expression he got, and this expression goes for a discrete energy levels. Now the atomic heat is given by this. Now the CV is the heat capacity. So when we differentiate the energy respect to temperature, we'll get the CV, that's the specific heat capacity or constant. So we differentiate this one respect to temperature, we'll have, because we already saw it as it's related with 3R here in this equation. Let me go back to that one, you see it. You see, so we have 3RT is the same as 3NKBT. So when we are having the 3NHU, because it's a quantized, this one is not a quantized form, but this is a quantized form of it. So this is the same as this. So you factorize the constant out. 3 is a constant, the gas constant 2 is a constant. So it's not dependent on temperature. You can take them out of the integral. Then when you do that and you differentiate what is in the bracket, and you are differentiating with respect to T. Okay, but because yes, yeah, so this term is a constant term. The 3N nu V, H nu can be taken out and you'll be left with what, 1 over whatever that is there. Then when we differentiate the exponential function, we'll get what is here. So we'll get this. We'll get 3R, then we have this square, then multiply by this, all divided by that. So this will give us our heat capacity. And C, given by the above equation, decreases with decreasing in temperature. So when you look at the C is directly inversely proportional to the temperature. So once the temperature is increasing, then C will be what? Decreasing. So that is what they're saying, that C is given by the above equation, decreases with what? Oh no? Decreases with decreasing temperature. It is not decreasing with decreasing, because this is the index. So if we square C, this is going to be high. So it should have been decreasing with increasing temperature. Because if you look at the mathematical expression, the C and then the temperature are not directly proportional. Okay, so let's check the exponential. This one will give us a decay. And if you check, if you increase the T, let's just look at the exponential alone from this denominator. Assuming we increase the T, so your denominator is going to be large. Okay, we are not varying the frequency, we are not varying the Planck constant. So once you have a larger denominator, it means you will be getting it to be approaching 0. And any number raised to the power 0 is 1. I don't know whether you are getting what I'm saying. So if this T is increased, so T multiplied by a constant. So for instance, if I take T to be 100, then the value I will get will be small if I take T to be 200. You understand? It will be greater if I take T to be 200, because this factor, the denominator factor, is going to be large as T increases. So once the denominator is increasing, then your value is going to be what? Small. And so that will be given as a smaller value here. The same thing when you come to this point, the same way. So it's going to go with this T in the bracket. So it should have been, it decreases with what? Increasing T. Sure, it's a typing error. Okay, so that is it for the heat capacity of solid. So now, okay, is there something you want to say? Hello, somebody, microphone is on. I thought you were asking a question. Okay, so now they said you should define state. define, state the principle of equipartition. It should be either you state or you define. Okay, so you state or you define it. Now, briefly explain quadratic degree of freedom. That's why we talked about the translational, vibrational, and then rotational. Then prove that the average translational kinetic energy of a particle in a gas is this. And this is what we've gone through. Okay, that's the proof that we've gone through. So that is it. Try and then go over to see whether you get the same thing. Okay, so we are coming to section 3, which talks about Planck's radiation formula and then the Rayleigh-Jeans laws. And this one is just a recap from our modern physics. Hello, are we there or we are tired?
We are following, sir.
Okay.
Following, sir.
So we can recall that in the modern physics, we plotted the experimental data against frequency, and then we realized that the theoretical value was approaching the UV catastrophe at a very large frequency, but at a lower wavelength. Okay, so and which we are saying that the theoretical formula agrees with the experimental data, which was conducted by Planck, but that was at a higher frequency, but deviated badly at a lower frequency. So when you also define in terms of the wavelength, you see that it is agree with the experimental data at a very short frequency, but deviated badly at a larger frequency. So that is the Planck and then Rayleigh-Jeans law or catastrophe that we saw. So now Stefan Boltzmann's and then the Wien's and Rayleigh-Jeans law. So we have to first of all talk about the Stefan Boltzmann's law, which he says that the energy radiated by a black body is proportional to the fourth power of the thermodynamic temperature. That is what the Stefan's law says. It says that the total energy radiated from a black body is proportional to the fourth power of the absolute temperature. That is the expression there. So the U as a function of T is the energy, then the sigma is a constant, then T to the power 4 is the temperature, the fourth power of the temperature. So in a modern, we plotted a graph and we realized that as we plot energy against temperature. So as a temperature, we have a curve that is shooting up. If you can still recall, we have that curve. Now, what the Wien's displacement also stated was that he said that like the black body radiation curves that were picked at different temperatures at different wavelengths is inversely proportional to temperature. Okay, and we saw it earlier on the diagram that we seen with the changing in temperature. Yes, these curves. So that is what the Wien's talks about. The Wien says that the black body radiation curves. So these are the curves. The curves that are for different temperatures. So T1, T2, T3 they peak at different wavelength. So this one we plotted against frequency. So if you want, you can use the frequency. But you know that frequency and then wavelength are inversely proportional. So whichever way you want to go by it. So they peak at different wavelengths, which is what inversely proportional to the temperature. So for the wavelength, you see that wavelength, I'm saying that they are inversely proportional to what? Temperature. But for the frequency, since wavelength is inversely proportional to frequency. So when you define in terms of frequency, it will be what? Proportional. And that's why we're saying that as the energy is increasing, the peaks values are increasing in accordance with the increase in what? Energy. So that is about the Wien's displacement law or formula. Okay, and if you can still recall again, when we plotted the data, the experimental data conducted by plants, we have a bell shape, and we also have the value or the formula that was also derived by Rayleigh and Jane. Then we realize that as the values were agreeing with each other at a very long wavelength. So when you're talking in terms about wavelength, so at a longer wavelength, the theoretical or the predicted data agrees perfectly with the experimental data. But as the wavelength decreases, you realize that the theoretical data is shooting up. It tries to deviate from the experimental data, and we call that deviation as what? The UV catastrophe. So the bad deviation that occurs at a shorter wavelength when we compare the experimental data with the Western. So basically, this is the Boltzmann. So in 1884, Ludwig Boltzmann presented a proof of this result, which with the idea of pressure exerted by the radiation, and this law did not account correctly the energy distribution in the spectrum. Okay, so in 1893, Wilhelm Wien, through thermodynamics agreement, obtained the empirical formula. So we saw that in the modern physics that the constant which we're having, like B, is the wavelength is equals to B over the lambda, or the constant B is equals to the wavelength times lambda. If you can still recall very well, that was what we saw about the Wien's displacement formula. Yeah, it stated that when we divide the temperature with frequency, we get a certain constant, which we represented it as B. Okay, so this is the equation, and A and B are constant. So now we can get something. So let me read here. Where A and B from this equation, so where A and B are constants, now it explained the spectrum for high value of frequency, that is visible, and then ultraviolet region. So you know that when you take the energy spectrum, the visible regime and then the ultraviolet regime, they are having a higher value of frequency. And yeah, no, but not for low values of frequency. Okay, so when you come to infrared, no, what is this is miscommunicated, or because when you look at visible light, they have a longer wavelength, right? So once they have longer wavelength, they should have a smaller frequency, because the energy in the UV region and then the visible light is far less than in the infrared. But why are they saying that it explains the spectrum for high value of frequency into bracket visible and ultraviolet region? No, that should not be the case, because the wavelength in these two regions is rather higher. So once the wavelength is long, then frequency should be short. And once the frequency is short, it has a very less energy as compared to a higher frequency. So they are trying to say that infrared region rather has a low energy. Is that possible? Are you getting what I'm saying?
Yes. So what do we do? Should we take what is there, or you alert them and get back to it, or you should change it right away?
Yeah,
Because what
because
I think we understand, but if it is
Mhm.
contradicting what you have already done, then what's the way for it?
Because if you look at it, the statement here, infrared.
So restructure it the way you want us to, like write it. Then later maybe you alert them.
Okay, we'll look at it. But at normal circumstances, you and I know that the energy in the visible region is not high as compared to the infrared. So infrared, or is the other way. So when you take the spectrum, let me see. I have
Yes. I actually thought they had shorter wavelengths. Rather,
yeah,
those microwave regions have higher wavelengths.
I have a wavelength.
Yes, so it means that the frequencies will also increase in that direction. So from
So
microwave down to
mhm,
the ultraviolet regions, the wavelength is decreasing, whereas frequency is increasing.
yes. So but if you look at okay, I've gotten it. I've gotten it. So you see visible light up and then down. So down the visible light region that you will be having this your gamma, beta, and then those things. But up
Yes.
to you have that. Okay. So they are using the visible light as a reference, but the way you frame it, like it's right. So that is right. Okay, so this is known as the Wien's displacement law, stated as the wavelength distribution of the thermal radiation from a black body at any temperature and has essentially the same shape as the distribution. Okay, so these are just grammar. Okay, so let's move down and see. Okay. So from the results, the James and the James, their results, religions, they are having this. Now this is 8 pi frequency square times kBt over speed of light. So as usual, our kb is the Boltzmann constant. And then c is our velocity of the light in a vacuum. So equation 3.3 is a Rayleigh-Jeans law. And it did a good job only for low frequency. So at low frequencies, it agrees with the experiment, but failed at high frequency. So further, it has led to the total energy in the spectrum as this. So you see that when you do it at to calculate for the total energy, you realize that at a higher frequency, it will be approaching infinity, to be going to infinity. And that's why we are saying that it's moved towards the UV catastrophe. Now the spectrum diverges. So once it's going to infinity, it diverges. So the spectrum diverges at high frequencies. Then Paul refers call this phenomena as what? Ultraviolet catastrophe. So is this scientists that coined it as the UV catastrophe. Now this divergence was not observed experimentally. The disagreement of theoretical predictions with the experimental observations hinted that certain basic assumptions of classical physics were somehow wrong. Okay, so all these things are explanation to the existence of what? Quantum mechanics. So because some concepts were not clearly explained by the theory of classical physics. Okay, so now let's look at the Planck's radiation formula. Now, he also makes some assumptions. So he made two assumptions. So his first assumption is that he realized that the radiations that are emitted here changes. So when you change the energy in the radiator, happen to be what discontinuous and discretely. So he is considering the energy to what discrete, not continuous. That is one of his assumptions he made. And then two, he also assumed that within the black body surface, they are oscillating as what harmonic oscillators, or the body is made to oscillate like a harmonic oscillator. Now they have discrete energy. So he proposed the formula as this: En is equal to NHV. So where N is an integer, which is 0, 1, 2, 3, and so on. So when you are talking about 1, 0, so E0, that is the lowest energy level, will be 0, because if N is 0, you will have energy. Now, if N is 1, you have HF. Then H2 will be 2 times HF. If it's 3, it will be 3 times. So these are the levels. So 1, 2, 3, 4, level 1, level 2, level 3. So where the H is our Planck constant. Now, this is the origin of the concept of quantization. And then the quantization is that you are presuming that the energies are not in a continuous form. They are not like having like decimal numbers. So they have disjoint. So they have breaks in them. So one energy level to the other level. Now that is, oscillators have only discrete values of energy and are integral multiples of the energy, which is HF or H nu. Here, the energy is that of a localized particle, while frequency V is usually associated with a wave. When you talk about localized particle, it means that you presume that the particles are quantized at a certain location. They've been positioned. So that is a localized particle. So when you talk about the localized, it means that you don't have a specific position for the particles that you are looking at. So the particle is in constant motion. But when you are talking about localized, it means that they are, occupying a certain portion of whatever you are studying or examining. Okay. Now, the third assumption he made was that the distribution of oscillators in discrete energy states is governed by the Boltzmann distribution law, which we saw earlier on. So the distribution law of energy, the average energy, which is a function of frequency and temperature, denotes the average energy of an oscillator. Then you have this expression. So we have the expression of the energy to be this one. This is not the average energy, it's the total energy, to be equal to 8 pi nu square multiplied by the average energy contribution, or divided by the speed of light in the vacuum to the power 3. And you can't. So now we saw the energy, the average energy expression earlier on. So when we substitute it, we'll have this. So this will give us the total energy contribution. Okay. Yeah. So this is the Planck's radiation formula, what we saw up there. And I think we saw the same equation in our modern class. So that was what this equation was plotted, and that gave us a bell-shaped curve. So the results of this equation was what we are saying that is the experimental data. Okay, now the Planck's formula agreed remarkably with the experiments at low frequencies, and it becomes the Rayleigh-Jeans law. As Planck's discovery led to the formulation of quantum mechanics. Okay, so in all, the quantum mechanics came into existence because of like the findings that Planck got from his experiment or his predictions. So now we know that the size of the energy quanta is proportional to the frequency. So it's proportional to the, oh, who is killing us? Yes, Mr. George, your hand is up, sorry. You didn't see. Mr. George, your hand was up.
Oh, no, sir.
Okay, means it's long time. Okay. So what it is saying that it said like the energy is proportional to the frequency when you come here. Where is that? The radiation of the low frequency is easy to generate. Now here, Planck discovered that we know that the size of the energy quanta is proportional to the frequency. So when you look at this expression, you see that the energy here is proportional to what? The frequency, or here, the V. They're all proportional. So now radiation of low frequency is easy to generate because it needs only small quanta of energy. So we don't need much energy to be able to generate a frequency that are low. But for high frequencies, radiation requires large amount of energy. And all these things are coming from what? The relations that we have. We know that the energy is proportional to the frequency. So once the frequency is high, automatically energy will also be what? High. If frequency is low, you don't also need high energy to do it. So it is obvious from the formula. Now this accounts the explanation for the spectrum of black body radiation. And it is easy to verify that the ultraviolet catastrophe not occurs in the Planck's constant. Just a minute. Just a minute. Okay, so let's proceed. Someone is calling me. I just want to alert the person that I'm having a class soon. All right, so it is easy to verify that the UV catastrophe not occurs in the Planck's formula. Planck's idea of discrete energy of a harmonic oscillator implies that the frequencies for the absorbed and emitted radiation should be discrete. Yeah, so that is what he first of all assumed. So we talked about the discrete nature of the absorbing frequencies. Now, according to the classical physics, a system can absorb or emit any amount of energy, which is contrast to the work of the Planck. Because the Planck, we saw that the energy that is emitted by the oscillator is discrete or quantized. And then he coined this as the term like quantum for the packet of what energy. So quanta is just talking about a packs of what energy that have packs. So we call them a quantize or quantum. So all these things are for so. Now, what he did is that he proposed of this. In a classical physics, energy is a continuous variable, while in the new theory, it is quantized. So, means that in the classical physics, we treated the energy as what continuous. So we show that, and which is true when you send your mind back to a simple pendulum experiment. So when you swing the pendulum bob and you allow it to oscillate for some time, you realize that the motion slows down or dies out gradually until the particle comes to a rest. So assuming you continue pushing it, so when you drag it, you allow it to go and come, then you push it again. Once you continue adding the energy, there's no way that the system will come to rest. And so that is what the classical mechanics is having the like it's thinking. So once you continue to subject energy to the system, then the system will continue to work. So quantization of energy and certain other quantities such as angular momentum and spin in the new theory led to the name quantum physics or quantum mechanics. Max Born coined the term quantum mechanics. So these are just still backing up the history. Okay, so we look at the photon. We'll be talking about the photon. Yeah, a photon are particle-like quanta of electromagnetic radiations. So they are light particles, which are what massless entities. Now they travel at the speed of light with momentum and energy given by equation 3 by 7.7 and then 3.8. So the set of photon is what a particle-like quanta of what electromagnetic radiations. And one thing you should always know is that they are massless objects. Okay. Now this is the momentum of a photon. So this value you can see it as de Broglie wavelength, because if we are saying that light can behave as particle at the same time waves. So what de Broglie did is that, so he was also saying that then if matter can also be exhibited as what? A wave. So the particle nature of the light is what we term as the photons. So he also extend that one to matters and then subatomic particles, and then the wavelength is expressed. So now the momentum is given as P is equals to H over lambda. So when you make lambda the subject, that gives us our de Broglie wavelength. So where the lambda is the wavelength of the electromagnetic radiation, and in comparison with the microscopic standard, that is in the classical aspect of view, the momentum and energy of a photon are tiny. For example, the momentum and energy of a visible photon with wavelength 663 nanometer are P of the order of 10 to the power minus 27, and E is of the power of what? Order of minus 19. So you see that it's very, very small. These are decimal 0.000000 is very, very, very small. So 1 electrovolt is given by this 1.6 times 10 to the power minus 19 joules. So if you are having in joules and you want to convert to electrovolt, then you use this relation. We are also having an electrovolt and you want to convert to joules. So when you calculate for energy and then you have it in electrovolt, when you want to leave your unit in joule, you just multiply whatever you have with 1.6 times 10 to the power minus 19. Then when you also have it in joules and you want to take it to electrovolts, so you divide it by 1.6 times 10 to the power minus 19. So it's a useful unit for the energy of a photon. Visible photons have energies of the order of an electrovolt, and X-ray photons have energies of the order of 10 kilovolt. So all these things are, is there a factor? Kilo is a factor. The unit is just the electrovolt. So when you have it, you calculate, you can decide to write it in terms of any factor, whether you can leave it in kilo, mega, whatever. But the unit is just electrovolt. All right, so they are saying examples. So we just go through one or two and then we'll move on. So consider a green light source of 100 watts with wavelength of about 6 times 10 to the power minus 7 meters. Calculate the number of quanta of radiation being emitted by this light source. Now you are given the power, you are given the wavelength, and you need to get calculate the number of quanta, yes, the energy quanta that is being emitted. So you have to first of all define your energy, because energy has a relation with power. So now this is the energy of the photon. The value for the Planck constant is 6.626 times 10 to the power minus 4, and then that, then divided by the wavelength. Then this gives the energy in terms of joules. Now the number of quanta, that is N, emitted per second by the light source is given by this. N is equals to 100 times the energy, the wavelength divided by this. So this is not anything. It's coming from the formula we saw, that E is equals to NHC on lambda. So you just make N the subject. Okay. So when you do that, you will have the, oh, my battery is going down. Just a minute. Let's see before it goes off. Okay. So you see that earlier we saw, from where we were talking about the discrete energy level, we saw that En is equals to NHC on lambda. So when you make that N the subject, this is why you have the expression, because you're going to have this, and when you simplify, you get 3.03 times 10 to the power 20 per seconds. So in every second, you will have 303 times 10 to the power 20 number of photons being radiated or emitted. So that is okay. So this is self-assessment. You go through, you define energy in terms of classical mechanics, then quantum mechanics. Yeah. Yes, I think
Sorry,
someone has. Yeah.
I want to ask a question.
Come again.
So, I want to ask a question regarding the
All right.
question you just said. So,
Okay.
Can you scroll up small?
Okay. Okay.
So I see. Because I'm seeing two answers. I don't know whether they are similar answers. The first one regarding E is equal to HC. Oh, come. The first one, it is E is equal to HC over lambda. We got 3.3 times 10 to the power negative 19. Does it mean that we can use, like, looking at the two together, we can use this one to solve the answer, get the answer, or the first one to get the answer? I'm not
Yes. Okay. So you use the first one to get the energy. So the E is equals to AC over lambda is the energy of the photon. Okay, so the 3.3 times 10 to the power minus 19 joules is the energy that the photon is carrying. But the question is that we should find the number of quanta. So we are looking for N. Let me take you back small. When you go up here, we were talking about the Planck's system. So you see this equation here, equation 3.5. Okay, so
Yes, sir.
let's say the quanta is 2. So now you calculate for HF, then multiply by 2 to get your total energy at that quanta. But now they want you to rather calculate for N. So N, that's what you are looking for. So you make N the subject. So that's what they did. When you come down here, so when you come down here, there's just solve for the energy, because we know that F is the same thing as C over lambda. So instead of F, they substituted C on lambda. Then solve to arrive at E is equals to 3.3 times 10 to the power minus 19 joules. Now, how do we now get the distance?
Quantum.
So now, when you now substitute this one back to the equation that I saw you, I showed you up. So now your E is now this. That's the E. Now the Planck constant is still there. The C is still a constant. Now you're given a wavelength. The wavelength is this. Now the N is what you are now looking for. Okay.
Okay, thank you, sir.
So it's when you get 20, you see that there is no difference in the answers like that. There's no much different. Let me just say there's no different. There's no much different in terms of their factors, but this is negative and this is what? Positive. So you see that the value is almost the same thing, 3.3 and then 3.03. But this is to the power of 20, which is positive, and this is 19 because of this 100. And then 2, when you make E the subject and the subject, you have this one being a denominator. So that's if you are talking about the number of quanta, use this formula. So if you are talking about the energy, so you use this formula. So that is it.
Okay, sir. Thank you, sir.
Yeah, you're welcome. Okay. So you define the energy in terms of classical mechanics and then quantum mechanics. So you can write it down. Then state mathematically and in ways the following laws and explain all the parameters involved. So Rayleigh-Jeans, you write the Rayleigh-Jeans formula, Wien's displacement law, and the Stefan Boltzmann's law. We saw all of them. And you just explain the constant. So the grade 2 is here. So calculate the energy transferred by each. Let me read the question and then. It said in an experiment of a photons streaming from a lamp, the students estimated the power of a reading lamp to be 40 watt with wavelength this. Calculate the energy transferred by each photon and calculate the number of photons emitted by the lamp in each second. So you have to, the first one is you are calculating energy. Okay, so you substitute, find your frequency. This one they are solving step by step, but you can just write the formula, add the C and lambda and substitute them and solve. So here they solve for frequency, then they use this formula to get the E. You can equally substitute the C on lambda in place of F, use it with the Planck constant to get the energy, which is 4 times 10 to the power minus 19 joules. Now the energy per second. So when you take energy divided by time is what? Power. Is that not it? Are we together?
Yes, sir.
Because power is what?
Yes.
The rate of doing
Rate
work.
of doing work.
So now the energy per second. So you just divide the energy that you have by second to get the power. So energy per photon is this, 4 times 10 to the power minus 19 joules. So the photons per second That will be the energy per second divided by the energy per photon. So now we have energy per second to be 40, and then the energy per photon is what? 4. So know the difference. What you calculated here is the energy for a photon, because that is what we say. This is the photon energy. So this value is the energy for the photon. Now, but per second will now be divided by the time. So that will give us our power. So you have it by time. So calculate the number of this. So you use the power. So here I think let me see something. The power is given 40 watt. Okay. So now this is the power. This 40 per second is the power. That's a watt because we're giving 40 watt. So this is the power. Now the energy per photon is what we calculated for. Now to get the photons per second will now be the energy per second divided by the energy per photon. So that's going to be power divided by energy. And that is what we'll get. We'll get 1 times 10 to the power 20 photons will be emitted in every seconds.
Please say, how did we came by the energy per second?
The energy per second is our power, and it's giving us 40. No, the unit for...
Was it stated in the question?
Yes, it's here,
Okay.
40 watt. 40 watt is here.
Okay.
So the 40 watt is the same to a joule per second. Okay, so that is it. So this is what we're trying to see. So if you look at the wavelength, yes, so above the visible light, we have a shorter wavelength. You see it? We have a shorter wavelength. So once we have shorter wavelength, we're going to have a higher frequency. So higher frequency means higher energy. Then violet is giving us 420. Then the infrared will be down. So that one is increasing. Okay, so what the statement that we're contemplating is right. So microwaves, radio waves, and then goes down to infrared and those things. So those one will have. This is centimeters, nanometers, meters. Okay, that's fine. It makes sense.
Sir,
Yes.
I'm saying yellow light, red light. So which one is the
Yeah.
visible light?
Which one is it? Visible.
Yeah, between the
The
yellow and the red.
The visible spectrum is where you and I can see.
On the table.
Yeah. And you're saying that you are seeing what?
Yellow, red light. But we have visible light as well, but I'm not seeing visible light here. So I don't know whether they are using another one in place of the visible light.
I didn't get your question, please.
Yeah, but in the spectrum we have visible light, right?
Yes, it is
Yeah.
the visible
But
region,
here,
the range.
okay.
So the visible light is just a range that we see things. You see, the human eye cannot see things at all wavelengths. So where you and I can see, and this is what we always term as the visible light range. Then, and this happened because of the sizes of the wavelength. Okay. . Okay, so let's also look at the particle dual nature of light. All right, I think somebody's asking a question. So kindly go ahead and then if someone raises his or her hand. Okay, I'm sure somebody left. I thought it's a question. Okay, so we've been talking that light can behave as a wave at the same time as a particle. So what actually brings about these things? So we want to look at what instance can we say that light is a wave or a particle? So light can actually behave as a wave, and then it can also be a particle. And based on what some circumstances, how or where you are looking at it. So in the classical mechanics, waves and particles are two completely distinct types of physical entities. Yeah. So when we are looking at it at a classical point of view, there are two contradictory things. They are not the same thing. But waves are continuous and spatial, extended, whereas particles are discrete and have little or no spatial extent. So what we are saying is that you and I, we see that waves, when we see a disturbance, maybe on a water surface, we see that the ripples are continuous. Okay. Then when you talk about particles, particles are things that we can actually count them individually. So when you talk about like grains, maybe granite, they are discrete. Okay. So you see that classically, you can say that they are not the same thing. But when you come to the subatomic level, you realize that they are same. So it's like when you use your pen on the paper, so you can use a pen to write a wave or a sketch a wave front or pattern. But let's say you start touching your pen on the paper. So you see, first mark, you see it as 1. Second, you see it as 2. Third, you see it as 3. But let's say you continue to do that for some number of marks. So you see that the marks become what? Cluster. So though it's still like you are pointing them 1, 1, 1, 1, 1, 1, 1. So assuming like as you touch the paper, you are counting. By the time you count to 1,000, just around maybe a small area, you see that 1,000 individual points that you are, they will come together and then look as if what they are with, like they are something you can, distinguish or differentiate them again. So they will be joining each other as you continue to touch on the paper. So on the quantum point of view, you can see that those were particles, like they were points that you were just, pointing on the paper. But as you do it for some time, it becomes like they are joined together or combined together. So you can say that, okay, they can be seen first as like waves, particles, but now you are seeing them as what? Waves. Okay, so however, in quantum mechanics, waves sometimes act as particles, and particles sometimes act as waves. This strange behavior is known as wave-particle duality or dual nature. Now, in this session, we shall examine how wave-particle duality shapes the general features of quantum mechanics. De Broglie waves will also be discussed briefly. Okay, so that is what we are expecting, and we have our expected objectives here, just as I read. Now, let's look at the de Broglie waves. So, in the absence of external forces, such particles of mass m, energy E, and momentum P move classically in a straight line with velocity. Okay, so that is what we learn in the classical mechanics. So when we are considering a particle to have zero net force, okay, so you expect that to move freely in a straight line. So let me say something small about what de Broglie said about. So his contribution is that he said if the where is that? If I want to give you a definition of what. So yeah, so what he proposes that he probably says that just as light has both wavelength and wave-like and then particle-like properties, electrons and then for that matter also has what wave-like property. So that was de Broglie contribution. So he extended the particle dual nature of light to matter. And matter, you talk about the subatomic particles, atoms, electrons, and then so now in the classical physics, this is the expression of the momentum. Momentum is equals to mv. So when we make v the subject, we have the velocity as equation 5.1. Now, and this satisfies the relationship between the energy and the momentum as this. So this comes from the kinetic energy. When you take the kinetic energy, which is half mv squared, so the half mv squared, you try to multiply by 1, and you decide to choose your 1 as m over m, because any number divided by the same number is 1. So kinetic energy, which is half mv squared, then you multiply by m over m, then you can transform that kinetic energy to this. Because if you multiply by m first, this is half mv squared. So the numerator will be m squared v squared. So you can write all of them as mv all squared. Then your denominator, which is now half multiplied by m, will be 2m. So, but we know that p is equals to mv. So mv and then everything square, you can remove the mv and put the p square, and you have this. So this is how the relation between the kinetic energy and the momentum came about. It's just about multiplying the kinetic energy by 1, and your 1 you choose to be mass over mass, and then you manipulate, you will get this expression. So just as light waves sometimes exhibit particular properties,
So please, can you
yeah.
go over this one, this part?
Oh, what I'm saying is that if you can try, write the kinetic energy, which is half mv squared, then multiply by 1. The 1, you take m over m. Any number divided by the same number is 1. So 2 over 2 is 1. 10 over 10 is 1. So we are taking m over m. So it's 1. So when you take m over m, multiply the numerators and also multiply the denominators. So already the numerator will be mv squared times m. So m times m will be m squared v squared. Then the denominator will be 2m. So if I have m squared v squared, I can write mv all squared.
Sir,
Yes.
sir, we will be grateful like we were doing then. You'll be writing something on the board so that if possible we won't know. But already we find it difficult to interpret or understand what you are doing, please.
This is not anything complicated, that's why. What I'm saying is that see, when we get to something that I know at least is a bit challenge to you, that is not anything. It's just like mathematics. Just manipulate. But let me show you what I'm saying. Can you see the screen? What I'm saying is this.
Yes, please.
Can you see? Can you see, please?
Yes.
So what I'm saying is that we have kinetic energy is equals to half mv square. mv square. This is kinetic energy. Now I said we should multiply this one by 1. I multiply by 1, I will choose it m over m. Because if I have 2 over 2 is 1. 2 over 2 is equal to 10 on 10. It is equal to 100 over 100. And everything will give you 1. So I am choosing my 1 to be m over m. Because m divided by m is 1. So you will now multiply m times m will give us m squared. Then v squared. Divided by 2 times m will be 2m. Then I can write this one as mv all squared over 2m. Please. Who is this? Mark. Who is Mark? Mark.
Sorry, sir. It was a mistake.
Okay. So now we have this, but we know that P is what? MV. So instead of this MV, we put P there, but this is energy. Energy, kinetic energy. So you just put, so your E will now be equals to, instead of MV, you put P, but it's squared. So squared over what? 2M. So that's what you are seeing there. Okay. So this is a kinetic energy and then momentum relation, how they relate. Okay, so this is what I was saying. So when you do it that way, you will get the energy to be P squared over 2M. We'll do this. You have to take note of it, especially in the classical mechanics. So classical mechanics, these are some of the things that you will be dealing with.
Hello, sir.
Yes.
Please, I wanted to ask with the same let me say formula adjustment. Okay. There is also a where we can have KE. I mean, looking at the relationship between KE and then momentum, we can also have E equals half PV. And I wanted to know whether that is also relevant in the kinetic energy and then the momentum discussion.
We can also have E to be equals to half.
I mean,
P
was half PV.
PV. No, it can't be possible. Either you have it this way to be FV, then this way will work. So I think this way will work. Either FV. So let's see something. Okay. What is the unit for energy? It's joule, right?
Yes, please.
So joule, and once it's joule, you can use any other energy to check the unit. So if you use work is energy, right?
Yes, please.
So what is the unit for work? The formula for work is force times what?
Distance.
So force times distance. So F times S. What's the unit for F? Newton. And what is the unit for S? Meters, right?
Yes, please.
So Newton meter. So let's see whether we'll get the same thing there, what you are saying. So what is the unit for momentum? Momentum is what? Kilogram meter per second, right?
Please.
And what is the unit for velocity? So times meter per second. So if you are going to multiply them, this will give you kilogram meter square. Meter square, then per second square, right?
Yes, please.
So per second square. Now, but Newton is what? 1 kilogram meter per second square. Is that not it?
Yes, please.
Okay. All right, I think it'll work. So 1 kilogram is this meter per second. So meter, okay, it'll work. That's it. So dimensionally is correct.
All right, thank you,
Okay.
sir.
Dimensionally is correct because when you do it, this one can be written as 1 kilogram meter per second square times another meter. And this is Newton, this is a meter. So it's correct dimensionally.
All right, thank you,
Okay.
sir.
You're welcome. Okay. So we were talking about the Broglie wavelength. Yes, is there a question or somebody that has left? Yeah, if there's a question, you just prompt me, let me know. Because I'm not on the same side that there, so at times I won't see it. All right, so now, so it satisfies the energy and the momentum relation. Now, we can write the de Broglie wavelength. So what it is saying is that the lambda is equals to h on p. This is the de Broglie wavelength. De Broglie wavelength. So where the lambda is the wavelength, h as usual, Planck constant, then p is the momentum. So he related the momentum with that. Okay. So we can also write the momentum as this. So momentum is equals to hk. Yes, and this one is also coming from here. How do we transform this onto that? K is a wave vector. Now, from the normal waves, we always say the displacement of the wave is equal to the amplitude times sine, in bracket, it can be sine or cos, omega t plus k or phi. Okay, let me use this. Where we say k is a wave number and k is defined as this 2 pi, depending on the direction of the propagation, whether x or whatever, over lambda. So now, if I say from de Broglie wavelength, lambda is equals to this, I can also make lambda here because we want to factor in lambda. So at the end of it, we have momentum, h cross, h bar, and then k. So I'll make lambda in the wave number. So my lambda will be equals to 2 pi over k. The x is just showing the direction. X is a vector showing you the direction you are talking about. So this is lambda. This is lambda. I will equate it to. So 2 pi on lambda. Oh no, on k, sorry. 2 pi on k is equals to h on p. So let me make p the subject. Oh, on p. Let me make p the subject like this. So I'm going to have p to be equals to h, then this k is multiplied by this, divided by this, then over 2 pi. Okay. So here you can relate this one to the reduced Planck constant. We know that h cross bar is equals to h over 2 pi. So instead of the h over 2 pi, here I'll put h cross there. So it means your momentum will now be equals to h cross k. This is how you relate momentum. And then the wave number together. So in your book, yes, when you look at equation 5.6, is a typo error. There should be, so they type the correct one in 5.7. There you can see it. Okay, when I get back to that place, I will show you. But let's also see, initially somebody asked the energy of a photon, and I was saying that you can either write it this way, HF, which is the same like HC on lambda, or you can say H is equals to what? H cross nu. This is what we call the reduced Planck constant. Please take note, it's not the same as the 6.626. No, Planck constant. When you are solving problem, look at the constant very well. Don't use H for H bar. They are not the same thing. Their values are not the same thing. So when you are solving, watch out. If the equation you are dealing with is H cross, don't go and use 6.626 times 10 to the power minus 34, sorry. Don't go and use this for H. When you do that, your substitution, everything will be right, but your final answer is going to be wrong because you are not using the correct constant value. So if you want to also make a transition from E to this, someone microphone is on. Okay, I think it's Mr. Ibrahim. Okay, so you can do it that way here. This one, PowerPoint. Okay, see, yeah. So we can do it that way. Now, we define E as what? HF. Okay. Now, you and I know that omega is equals to 2 pi f, right? So I will make f the subject here. Then this will be omega over 2 pi. So I'll take it back to this equation here. In place of f, I'll put omega over 2 pi. So my E will now be equals to h omega, then is divided by 2 pi. But we saw that h cross is the same thing as h on 2 pi. So in place of h on 2 pi, I'll put h cross there. So I can also write my energy as h cross multiplied by omega. So this is how you can also express. So depending on whichever constant that you were given, you can calculate for the photon of the energy using any of these two formulas. So either you go with this, that is, you will be going with this if you are given angular frequency. Okay, so you are given the angular frequency, you can go straight to substitute by using this formula. If not, you have to now define this way: omega is equals to 2 pi f. Then you make f the subject to get the value. Then you now come and substitute it in this equation to now solve for it. Okay. Okay, so that is it for that. So now we can make substitution for this one. So if you look at our equations that we have, the 5.6 that I was saying, they just have V is equals to HK. And then, yeah.
Okay. So the reduced Planck constant, we don't have the constant value.
Oh, the constant value is there. It's 1.0 is there. So if you want, just take a calculator, take the 6.626 26 times 10 to the power minus 34, then divided by 2 pi, whatever you will get. That's the constant value for.
And it's not on the calculator too.
Oh, the calculator is there. You look at it. I think it's constant. Constant what? 28 or is it 32?
Okay.
Or 18? Is it 18?
Please, on the regular ASU calculator, is 06.
06. Okay.
Yes.
So constant, then 06, you get the value.
The 06 is you know the normal blank constant.
So Francis, you just press Shift 7, then 06.
But that one I'm saying that on the 06, I'm seeing that the normal blank constant.
Yes. So then you divide the Planck's constant by the 2 pi. That will give you the H cross.
Okay.
Now, if you check, that one will be on the calculator.
That's what I want.
Look at the calculator, you see it. I'm not having a calculator here to confirm for you, but
on the regular
the symbol should be there, or it's not there.
I think Shift 09.
Okay.
Yes, it's
okay.
09.
It's 09.
All right. So can I go back to the PDF?
Yes, please, sir.
Yeah. What time are we closing?
4 p.m., please.
Wow. So
please, what is 3 p.m.? You have to go for break.
no problem.
Okay. It is even past the break time. So if it's even past, we should have gone for break for around 2 o'clock. Because now we are left with 1 hour, 10 minutes or 1 hour.
So if you are not tired, then let's close at 3:30 since we've used the break time.
Okay, let's do it.
That will be okay.
Okay. So you see that here. Now this one is just the de Broglie wavelength. Know that the de Broglie wavelength is generally pretty small, and for instance, that of an electron is this. So when you take the wavelength of an electron, this is what you will get. Okay. So it's 1.2 times 10 to the power. So 1.2 nanometer multiplied by the electron volt, and you take square root of it. So you get it to be very small. Okay, so you've seen the equation 5.8. That's what I just shown on the screen, and then I think the other equation is 5.6 or so. But you've seen it, so no problem. There's no need for me. Okay, so now for particle waves, now equation 5.2 and 5.6 combined gives the dispersion relation for such waves. So this gives a dispersion relation for such wave, and we have the omega to be equals to the Planck constant times the wave vector square divided by 2m. Okay, so now when you talk about the wave, we have what we call the phase velocity and then the group velocity. Now the phase velocity has to do with the portion or the direction of where the wave is propagating. And so then the group velocity will be the total or the collective velocity of the waves. Now this is the expression for the phase velocity. Phase velocity is the dispersion relation divided by the k, or the angular frequency over the k. So that is the phase velocity. So from here, you can have it to be p over 2n. P over 2n. That is the phase velocity. Oh, I've moved faster. It's jumped. Okay. Okay, so these are some work examples, and then now an electron has a de Broglie wavelength of this. What is its momentum? So you know the momentum and wavelength relate with a constant term, which is the Planck constant. So once you know the wavelength, yeah, you will know the momentum because h is constant, which we know. And then its speed. What is the speed? So once you know momentum, you know they talk about electrons, so you know the mass of electron. So you can use the classical mechanics to get the velocity. If it were to be photon, you just know that it's going to move with the speed of light. But this is an electron, so you use the mass of the electron, which is 9.1 times 10 to the power minus 31. So you do it to solve for it. Then when you do that, you have it as shown here. Oh, where's that when I press is jumped. Now the C says what voltage was needed to accelerate it to this speed. So you need an energy to give it a speed. Now with the frequency less than 0.005 C, then we can calculate the kinetic energy classically as this. So this is a kinetic energy, use the formula, then you get it to be 9.7 times 10 to the power minus 19 joules. Now you need to convert this to electrovolt, because that is what you need. You need a voltage. Now, which is converted to this 6.
Sir, please, are you on the PDF?
Yes, or I'm not showing it.
Yes, you are not showing it.
Oh, sorry. Oh. I thought I've gone back to that. So, okay, so what I'm saying is this. Then let me go back to the question. So the question gives the wavelength as this, and it is looking for the momentum. So this is the relationship between wavelength and momentum. So you solve for it. Now the second part is its speed. So you use the classical mechanics to solve for it. And I was saying that if it should be a photon, then you just know that it's going to move with the speed of light. But once it's an electron, you have to know that you use the mass of the electron. And you solve for it, you have 1.5 times 10 to the power 6 meter per second. So that would be the velocity that it will be moving with. Now the C part is what voltage was needed to accelerate it to this speed. Now, what is the energy given to the electrons for them to be moving with this speed? That's the meaning. Okay, so you have to solve for the energy. Then when you get the energy, then what energy that is driving it to move? So it's the kinetic energy. So it is moving with the kinetic energy. Once it's have the velocity, so this is the kinetic energy that is given to it to move. So you calculate for the kinetic energy. Then since you want voltage, you need to convert this to volt. And the beginning of the class, I said, when you have it in terms of joules and you want to get it in electrovolt, you just divide it by 1.6 times 10 to the power minus 19. So I also have it in volt and electrovolt, and you want to change it to joules, you multiply. So doing that, you have 6 volts. So this is the energy in terms of voltage or electrovolt that is given to the electrons to be moving with the speed of 1.5 times 10 to the power 6 meter per second. Okay. So we are coming to also, we are coming to also talk about the wave particle dual nature. So the property of waves that explains the wave nature of the light is the interference. So it's interference that shows that the wave indeed, light indeed behaves as a wave. But the particle nature too, the concept that also explains that one is the photoelectric effect. So here, although we have just described the experimental evidence for the wave nature of electrons and similar bodies, it must not be thought that this description is complete or that these are any less particles. So a diffraction experiment with properties are manifested during the diffraction process and the intensity of the wave. So let me not waste time reading this grammar. So let's move down and see what we have here. So now this is the setup. So we use a monochromatic source of light.
Yeah, please. That's not, is the old page that is there where you have moved to? The setup that you are saying is not displaying here. Is it the same? Is it only me or for?
Maybe your network.
No, the same thing over here. The screen is.
Hey, what's the problem? Stella is not moving.
Yes.
Let us see. Has it changed?
No, sir.
Oh. Okay, so let me stop. Let me sharing and go back in this. Still came back as the first where it was.
Yes, please.
Yes, sir.
What's the problem? Oh, it's changing here.
So then stop sharing and then reshare again.
That's what I did. And then come back and then. Has it changed, please?
Yeah, it has changed.
Okay.
But this time it's very wide. You are seeing two things.
I will change it.
Okay.
No, it's fine.
Yeah, it's all okay.
Okay, all right. So yeah, there's a diagram that I was talking about, the setup. Now this is an experiment that was conducted to actually prove that light can behave as a wave. And I said the property of light that explained immediately that it is indeed a wave, is a wave is interference. So we have a monochromatic system or light source. So monochromatic light means a light with a single wavelength. So we have slit 1 up to 4. Now the slit is just an opening space or an aperture that allows light to pass through. So we have the light going through the first slit. And the first slit is to slow the neutron beam from cold source. So the light source that they are using is a neutron beam. Now the second one is there. Now we have a prism which is made up of cuts, and this is placed at an angle of 120 degrees. So what the prism does is that it refracts the light through the entrance slit into the optical bench evacuator. Okay, we have an evacuator light tubes. So the angle of the prisms has to position such a way that it's able to direct the incoming light into the evacuator. So, but no, when you are doing as well, you have to calibrate, make calibrations because you want to draw conclusions. So if you don't calibrate, your results will be vague. So now these are the calibrations that were made. Then they have a counter at the back. So everything here is connected to scanning microscope. So let's see what was observed at the end of it. So when they printed out the effects, it gives a graphical outlook, and we have the intensity being plotted against the scanning slit. That's slit 1 up to whatever they have. So we have this picture here. So you see the intensities are not regular. So some you get as high peaks, then low, high in that order. So from the beginning, it is started like normal, then gets to a point it started increasing so on. Then until it has the highest, recorded the highest peak at this point, then decrease it again. So you see that it is a normal shape. Whatever happens at the beginning is what ends at the latter part. So it's symmetrical. Because if you stand at the highest peak, we can divide it into 2 equal parts. So it means that it is symmetric. Okay, so that is the experimental data that was obtained from the experiment. So a typical experimental arrangement is shown in the A, and the slit arrangement is illustrated. So just giving us a description of what was there. Suppose we now change this experiment by placing detectors behind each slit instead of a large distance away. This will detect individual neutrons passing through one or other of the slits, but never both at each. So saying that when you put a detector to find out how many neutrons are arriving. So you only detect one at a time. So a neutron arriving at a slit, one at a time. You can't detect at both ends. So that's what the statement is saying here. So it says that these will detect individual neutrons passing through one or other of the slits, but never both at once. And the obvious conclusion is that the same thing happened in the interference experiment. But we have just seen that the interference pattern is formed by a wave passing through both slits, and this can be confirmed. This can be confirmed by arranging a system of shutters so that only one of the other of the two. So the experiment is just to show that the light behaves as a wave. And as I said, the property that best explains that is the interference patterns. So the interference has to, before light can be interfered, it must be coherent. So we know the meaning of coherent light. We talk about monochromatic, so that's why the source has to be monochromatic. So when you talk about coherent, it means that the light is in phase. So they're in phase, they're coming from a common source, then there is never lag. There's no lag in between them. So that is the setup.
Hello,
Now,
sir.
yes.
Sorry, please. I wanted to know, is this experiment similar, or let me say, would the Young's double slit experiment also achieve same purpose? And then
Yes.
second, oh, okay.
Okay.
And then secondly, what is the significance of the 120-degree angle of inclination?
Okay.
All right.
So the Young's modulus and then this one, they all explain the same concept. Because the Young's double slit experiment also shows that light behaves as a wave by using interference patterns. Yeah. So the slits, the opening of the slits are able to give the wave front to interfere. So you realize that where the holes or the aperture is, we have a low or narrow interference, but outside, then the waves begin to superimpose them. So it means that they all explain the same concept, which is what? Interference. Now the angle is just to focus the beam through the evacuator chamber. And so that is the purpose of the prism, and then the angle that is being tilted. Because if it is not positioned in that manner, there's no way that the beam will be directed through. So depending on the arrangement, so that is it.
All right, thank you, sir.
Yeah, you're welcome. Okay. So the rest are just is giving more emphasis to the setup. Where is it? Let me see. So let me read this paragraph and then we jump. So an alternative view, which is now the orthodox interpretation of quantum mechanics, is to say that the model we use to describe quantum phenomena is not just a property of the quantum objects, the neutrons in this case, but also depends on the arrangement of the whole apertures. Apparatus. Now this, if we perform a diffraction experiment, so that is a Young's modulus that you talk about. If we perform a diffraction experiment, the neutrons are waves. when they pass through the slit, you see. So there will be a wave after passing through the slit, but are particles when they are detected. So on detection, like when you use a detector, you see them as what? A particle. But from the slit, they will be seen as what? Waves. So it's like a human being and then its shadow. So your shadow will use interference pattern, but you yourself will be. Oh, just a minute. Someone is calling my name. Hello. Yeah. Oh, sorry. Okay, so that's if we perform a diffraction experiment, the neutrons are waves when they pass through the slit, but are particles when they are detected. But if the experimental apparatus includes detectors right behind the slits, the neutrons behave like particles at this point. Now, this dual description is possible because no interference pattern is created in the later case. So once the detector is, just as I was saying, when you begin to put a mark on the paper with your pen. So the mark that you are putting, they will be seen as the neutron, the particles that it is talking about here. But as you do it, you see the pointing, the way you will be touching the paper, your pointing will be like one after the other. But when it becomes cluster, it behaves like the wave. You can't see the distinction between the individual marks. So the detector will detect the neutrons as discrete object, but the interference we also see them as what? As it passes the slit, you will record it as a waves. So that is how we concluded by saying that light can exhibit as a wave at the same time as a particle. So now this dual description is possible because no interference pattern is created in the later case. Moreover, it turns out that this happens no matter how subtle an experiment we design to detect which slit the neutrons passes through. Now, if it is successful, the phase relation between the waves passing through the slit is destroyed. So let's move on. All these are just talking English. Okay, so let me see. So many of the apparent paradoxes and contradictions that arise can be resolved by concentrating on those aspects of a physical systems that can be directly observed and refraining from drawing conclusions about properties that cannot. Okay. So one thing about quantum mechanics is that is predicts in the future or things. So when you see something happening right now, so you want to see what will be the behavior of that thing in some time to come. So you will be calculating things which you don't know, you yourself, you will not be in the future, but you want to know what is going to be in the future days. So that makes it too abstract. So these are work examples. Once they provided a solution, it doesn't matter of going through them. Okay. So let's look at the last session of this unit. So we'll talk about wave packets, determine phase and group velocities of wave packets, and then state the Hesberg uncertainty principle and solve simple related problems. So now we talk about the wave packet. Now this is a picture of a wave, and it depicts like interference. So where you have the ripples shows that, so let's say if you use a double slit, so one slit is where you don't have anything showing at the left, and then the other one at the right. But where the waves that are coming out from one slit and then the other one interferes is where we have the highest the wave fronts, and then we have the highest peak there. So this is a wave packet. Now we can construct a wave packet in which the waves interfere with each other almost completely outside a given spatial region. We thus obtain a localized wave packet that can be considered an approximate description of a Pascal particle. Now, a wave packet consisting of a superposition of plane waves may be written as this. So when we talk about superposition in waves, is the addition of two or more waves. Now, one thing we should recall is that talking about interference, we have like two types of interferences. We have the constructive interference and the destructive interference. So depending on the direction of the movement of the waves. So if the waves are moving in the same direction, and these waves, they have the same amplitude, they are coherent. Now, the moment they superimpose, then the resultant waves is going to be higher than the individual amplitude. So the amplitude of the resultant waves will be higher than the individuals. So, but if they have the same amplitude and they move in the opposite direction, so once they superimpose, then we'll have a destructive interference, because the positive will cancel the negative and the wave will dissolve, so you will not see the wave pattern again. And such interference is what we call the destructive. But in the case that they will sum up and the resultant amplitude is higher than the individual, that's what we term as the constructive interference. So now this is the wave packet equation when they impose. Now we have the distribution as a function of displacement or position is equals to 1 over pi, 2 pi raised to the power 3 on 2 integral of J as a function of the wave vector, then e to the power I k r dk. Now k is the wave vector. Now the 2 pi on this talks about the volume. So you talk about the volume that it is occupied. Now this e to the power I is a complex wave equation. Okay, so that is how you write. So we will see these things further as we move on when we are talking about the Schrödinger equation, how to calculate the wave eigenvalues and then eigenvectors of a wave. So we'll be using the complex wave equation. Okay, so in a one dimension, it is reduced to what we have here, the same expression, but it is reduced. So this is in 3 dimensions. So the 2 pi, as I said, is equal. So now the evolution of wave packet is determined by the Schrödinger equation. Yes, and I said this equation earlier, I said that this equation is a fundamental equation in quantum mechanics, just as the Newton's second law or F is equal to ma is, the fundamental equation in classical mechanics or classical physics. So this equation we will be using not what is here. No, that is not the expression of the Schrodinger equation. We'll see it earlier on. So when you want to solve any problem, like you want to solve for the energy, you want to solve for the eigenvectors, you need the Schrodinger expression. Now, which we would be discussed in the next year chapter. When a wave packet evolves according to the postulate of quantum mechanics, the weights of the curves f of x and then g of k are related by this. Okay, so now when you take the uncertainty of the position and the uncertainty of the momentum, okay, it can also be represented as momentum. Then it should be greater than 1. Okay, so you extend this one to the de Broglie wavelength, that relation that we've seen earlier on, that momentum is equals to the reduced Planck constant times the wave vector. Now we have that. So the change in P here, change in X, it talks about the uncertainty of momentum, and then the position or displacement, or can talk about space. Now the uncertainty is that there is a small deviation. So for instance, when where the uncertainty comes in is that, let's say you are bonded, or your movement is restricted. Let me just put it that way. You are restricted to move between 2 places. So maybe from your house to your workplace. That is like your restriction. Apart from that, you are not going to anywhere, and you are moving constantly. Now, if I am here and I want to predict your location where you are, so probably I may predict that by now you are not stopping. Not that you are going to work. Maybe if you are teaching, I know school closes at maybe 3. After work, I presume that if you don't have any other assignment during your school, you should be at home. That is, if you are restricted, like just between home and then school, no other place to go. So it's not like that. So you are in constant motion. You just go to the school, go back home, go back to school, in that order. So my prediction may be that you are in school, but maybe probably you are not in school. You may be in the house, or you may be on your way back to the house, or you may level some distance to reach the school. So at the time I predicted, then, so if my predictions is not right, then it is what? Uncertain. And so you have the uncertainty in terms of your momentum. So once you are moving, then you have velocity. So that is where the momentum is coming in. Then your location is what we talk about, the space, or the position. Okay, so that is about the Hansberg constant. So he's saying that there is no way you can simultaneously predict or determine both momentum and then velocity accurately at the same time. So the more accurate one will be, the less accurate the other will be. So if the momentum is correct, so it means that when I say you are at this point, it means you stop, because when you are coming back from school, you must stop and turn. So if I predicted that you stop, you are at your house, it means that your momentum is 0. But once you stop, there's no velocity. And so, but if you are not also stopped, you are moving, then your location will be 0. I tell exactly where you will be. So just look at maybe a bee that is in a room, and then it is moving from one wall to another. So you can't actually give a number. So that is why there's a need for us to use probabilistic. So you bring probability. So when you take the probability, so you now have to quantify a location, and then So now you are no more giving specific location of the object, but you are giving a range that, okay, by this time, the person is within this range. And so then you can use that to now do your predictions and solve your problems. Okay, so this is the Hansberg uncertainty relation. Now, if we try to construct a highly localized wave packet, and I mentioned that the localized means a position it has been arranged at a certain place. So a localized, so a wave that is at rest. So when you know the location to localize a wave packet in space, then it is impossible to associate a well-defined momentum with it. Now, in construct, a wave packet with a defined momentum within narrow limits must be spatially very broad. Okay, so when you have a wave packet that has a narrow limit, it means that its space will be very big. So it means once this one is trying to be accurate, then the other one, the error margin is very large. Now note that since h is very small, now the notion of classical physics would fail only for microscopic systems. So we are dealing with minus systems. So that's the quantum systems. Now the uncertainty relation acts to reconcile the wave particle dual nature of matter and radiations. Now, considering a wave packet, one should differentiate between phase velocity and then groove velocity. So when we are dealing with that, and we already saw the phase velocity and then groove velocity, I said the groove velocity is a differential of the wave velocity, the phase velocity with respect to the wave vector. See it here. So now here for a wave of angular frequency, now you have a wave with this frequency defined as 2 pi f or 2 pi nu, and wave number which is defined as 2 pi over lambda. Now the phase velocity is given as this. So when you divide omega respect to k, so the 2 pi will cancel 2 pi, then this is divided, then it will come back and then become lambda frequency. So that is the phase velocity. Now this is the rate at which a point of constant phase travels through space. So constant phase travel through space, this is what you have. Now when a packet of waves differing in frequency and then phase speed combines to create a region of strong contractive interference. Now the speed, which is the group velocity or the group speed at which the region advances, is related to the angular frequency omega and wave number k of the component waves by the relation. So this is the expression of the group velocity. So the differential of the angular frequency with respect to the wave vector that defines the group velocity. Right, so I think our time is up, and then we are almost finished with the. Okay, so go ahead in the next question, please.
So it's not in relation to, I mean, what we are discussing. I mean, if we are done, then I have some questions to ask you in case you can help clarify things to us.
Okay, so okay, so we will end right now. Now this is the uncertainty principle. I've said this countless times. The definition is that it is impossible to simultaneously determine both momentum and then position accurately at the same time. So let's see. Let us consider the limit that wave particle duality places on the simultaneous measurement of the position and momentum of a particle. Suppose we try to measure the position of a particle by illuminating it with radiation of wavelength lambda, and using a microscope of angular aperture A as shown here. So we are using a microscope to do it. So you have this. So the fact that the radiation has wave properties means that the size of the image observed in the microscope will be governed by the resolving power of the microscope. Yeah. So depending on the resolving power, that will let you know the waves. If the resolving power is high, then obviously it will give you a better look of the wave. Now, the position of the electron is therefore uncertain by an amount of change in x, which is given by standard optical theory as change in x is proportional or equals to lambda over sine alpha. So that is that. Now, however, the fact that the radiation is composed of photons means that each time the particle is struck by a photon, it requires, as in Compton scattering. So the momentum of the recoil could, of course, be calculated if we knew the initial and final momentum of the photon, but as we do not know through which point on the lens then the photons entered the microscope, the x component of the particle momentum is subjected to an error. Okay. So since we cannot, tell the final and initial momentum, we can't, do it. So we have to take it as an error from the x component of the momentum as this change in px. So in all, we can write with the error then times the p sine alpha now give us our total formula as 2 pi h cross sine alpha over lambda. Now combining these two equations, we have change in x, change in p in the x direction, give us 2 pi, times the reduced Planck constant. So when we do everything that will come out, so actually this is how equation 6.10 is the relationship, the real relation or true relationship of the Hansberg uncertainty principle. So it says that the uncertainty that happens along the position direction and then the momentum direction is greater or equals to half of the reduced Planck constant. So when you recall, when I said the Planck constant is very small. So this relation is known as the Hansberg uncertainty principle. And according to quantum mechanics, it is fundamental property of nature that any attempt to make simultaneous measurements of position and momentum are subject to this limitation. So it should be noted that these results are independent of the mass of the electron and therefore are not a result of the electron recoil. Okay. So take note that it doesn't depend on mass. Now they would apply equally well to a particle of large mass, which would not move significantly as a result of photon scattering, although its momentum mv, where v is the velocity uncertainty would still be given by equation 6.7. Now the Hansberg uncertainty principle is more subtle than the popular idea of the value of one property being disturbed when the other is measured. Okay, so all that it is saying is just try to understand the mathematical expression of the uncertainty and what it means. What is the physics behind it? Okay. Okay. So you go through the work examples. Let's go through them. All right, I think we'll pause here. Then, God willing, I think tomorrow we will continue with the second unit. Yeah, any question up to this point on what we've gone through? If not, you will now ask this question.
So please, the last part, I will go through it so that maybe the next time we have class, you throw more light on it.
No problem. Yeah, any other thing? Okay, then you can ask your question. Yes.
Okay, sir. My question is in relation to the model that we are doing. First, I want to find out how many units are we supposed to cover all the units for this model, or for the 4 weeks that we are going to meet, you have specific units for us to cover. That's the first question.
And then the second, that's all.
And also, I want to find out, please, are you the one who is to handle us both mechanics, the classical and the what do you call quantum mechanics?
Okay, thank you. Yeah. So the first question is that whether we have certain number of units we will finish before the end of the semester, right? You see,
yes, please.
Per the model, we are supposed to always complete it before the end of the block, but because of the limited time, we are not always able to complete it. But it is better we do it with them. But wherever we reach and the semester or the block is over, then exams will be set on the units that we've gotten to. But it is always, advisable that if you are able to finish, because we are not like learning for only exams. And I think because of the issues of not completing some of the courses that, like when you see other courses that you're supposed to refer to, like it's still be difficult for you, because there are certain things that you have done them previously. Now moving forward will be difficult again. So let's see, because looking at the course content and then the number of weeks that we have, I don't think it's possible that we'll finish. But if we can finish it, it's better. So don't limit yourself in your reading. If you can read everything, it's fine, because it will help you. Then the second thing is whether I will take both this and then yes. So I will take you this into the classical mechanics. Yes.
So then, on behalf of my brothers and sisters on this platform, I'm not speaking because I have the mouth to talk to you. I'm speaking because we all want the best. Looking at how things have taken us from the first semester to the last block of which we have started. Things hasn't been easy for us. I'm talking about we physics major, we those who are majoring in physics, comparing ourselves to our colleagues who are majoring in biology, who are majoring in chemistry. We always cry. The reason being that we always find it difficult when the semester comes to an end. That's why initially I asked you the unit that we are supposed to cover, because the physics itself is something else. Now that we have gotten to know that, you are the one who is going to take us through the two courses, just like we're having you see, we also taking us the other 2 courses. We will be very grateful when it is getting to an end. Say, we beg you. For the tutorials is very important to us. Sometimes you go to the examination where you don't even know how to, you know how to even tackle the questions. As a matter of fact, you'll be fumbling, then the time will elapse. Then they will come and correct the paper. In other course, it's not like that. So we are begging for the sake of, we know we are teachers, we have family. Looking at the course, the volume, how comprehensive this course is. We are doing 5 courses this semester, this block, and it's very hectic. We are begging when it is time for the quiz and the semester, end of semester, please kindly do something about it. We beg you.
Well, I don't know what we meant by I should do something about it. I don't know. I don't know if you can explain further.
Like I was saying, you know, when I'm not trying to compare physics to other courses, but what I want you to understand is that, you know, some area that we are majoring physics and minoring chemistry. So meaning we have done chemistry courses. Sometimes, you know, our lecturer will give you tutorials, majority of tutorial for objective tests. Then if you are able to go through for a quiz, you should be able to answer with it. Only those who will not study or who will not be ready to learn. The same thing applies to the end of semester. If only you are serious student, then automatically you should be able to get something to write. But in the case of, physics, that's not what we are experiencing, or that's not what we are seeing. That's what I'm saying.
Yeah. Okay, but if you check most of the questions, if ratings of like the previous courses that we did, I think most of the exams are more or less like past questions. See, I understand what you are saying, but the thing is that physics itself is not a course that is easy. And then if you are not able to pick it during maybe lecture, and then after that you are not also having time to go through, even you go and see the thing that you know you understand, but a formula will make you get it wrong because you've not like practiced it. Because of like the nature of the program, or no, let me say the subject in this physics as a whole. That's why it is difficult, and at times too you can see the question, you go and then something small will be changed, and once you've not studied for understanding, then maybe you just go through as a past question. That small thing that has been changed, you can't find your way out. And I think maybe most of you are not also having maybe physics background. That's why the whole thing look complicated. Or maybe you did projects way back. So even the basics that you're supposed to build on, you've forgotten them, and then you have to now start from that one before. And the time to is not there for you to do that. I think that may be the reason. If not, so far the exams that we have been, if I'm not like lying, I see like most of them you see like some past question in it. Or this one there is a lie that I'm telling.
Oh, so we can't say you are lying. I can never say you are lying, but just
Oh
that.
no.
But I'm speaking as a whole. I'm talking about the general physics perspective,
Oh
not
yeah, I understand
you.
Oh no, I understand. Maybe you are just making all the exams. Yes. Thing is,
Sir,
yeah.
we see it to be past questions, but sometimes you can even get a past question a day before the paper, or that very day we are having the paper. Yes.
Mm,
So you after the exams before you realize that it was a past question.
that's question.
And then what my brother is saying is very true. It's very, very true. So please, this time around, we'll be very grateful if you could do something about it for us, as he said.
Okay, so that one, then we have to work with the coordinators. At times, we are the people teaching, and then there are certain questions. So at times, they will consult us. Okay, you're good. Where have you reached? So you will know like where everybody has reached before they set the questions. And at time to if maybe that coordination is not there, that's what maybe you see the questions and then you are not able to get to that unit before the question was set. But as you said, I heard you and we work towards it. And just as you asked of the unit. Now I think this time around it's only like online. We don't have face to face and then online where somebody will be teaching. Maybe this person is teaching this unit, another person is also teaching, and so at the end of it all, it becomes difficult for setting of questions. But now that it's like one person, so if I say, okay, I have gotten to unit 2, it means that all of you have reached unit 2. If we are gotten to unit 3, it means that everybody has gotten to unit 3. I think that one is going to be like something more better than the previous ones, because the previous ones we are many who are teaching, and this person is teaching this group, another person. So at the end of it all, there is no way we can be at the same pace. I think I've gotten what you said, so we'll see what to do. So is that like so past questions that you want, or you want like questions just to try your hands on?
Sir Festus.
Yes.
Good evening.
Hello, good evening, Felicia.
I didn't I take part too. I just joined. I went to wedding. So you have to teach me later.
Why you went to wedding? Why didn't I enjoy alone?
Oh, I didn't enjoy you. Right after the wedding, I didn't go to the reception and I came. Let me buy a movie and marry you.
We are learning you. You are enjoying yourself at wedding.
Me and you, dear, we know ourselves. You will have to teach me in the morning too. But Sir Festus, during the quiz, the quiz 1, there was something that, let's say this equation here, the way it reflected in the online quiz, me, I didn't see anything. All those I didn't now, or yeah, I mean, how I see it even over. If my colleagues can bear me witness, the way it was, I don't know whether it was scanned or it was, I don't know. So I couldn't see all those. The honest Obama, you have to get there. You have to be able to read that one before you can solve it. But me, those of us having the fourth eye, I couldn't see anything. It was faint, and then I don't know. I see to be able to my friend, you can help me how it was, no. And then those things, there were many in the questions. To some of us, the quiz 1, the and single numbers.
Oh, that's
But
Hello,
this
sir.
there is no
May I
easy.
make my submission?
yes, please.
Please, I don't know if it is possible, but if you can talk to the coordinators on our behalf, especially the first quiz. Sometimes 21 minutes, you are supposed to solve 20 questions, and that 20 questions include 15 or 14 calculation questions. Hey, say how possible?
Abnormal.
It's like they just want you to
It's
stay
abnormal.
little and then just shade, just highlight, select some of them and then submit. Because if you make an attempt to calculate, you would have ended up using 5 minutes to solve one question, or 10 minutes to solve one question. Some of them, they are standard session B questions. So some of them are standard session B questions that they are asking you to use 20 minutes to solve a variety of such questions.
No.
So I don't know. So
That's
now we stick
constant
lotto.
stream.
You finish and then you are getting 1, 2, 7, 8.
That's constant stream.
Oh,
Imagine questions, online questions without constant. And for 20 multiple choice questions, you set about 14 or 15 calculation questions. And you expect the student to work within that range.
So,
this is very sad.
What for this one there, I can't address it here, but what I would suggest is that I think maybe we'll have to find a time that we can meet them. Then we all we share with them our grievances. So things that we think it is not helping them. Well, like I agree with you. Physics question, objective questions goes for 20 minutes. It's not the best. At least if it is like 30 minutes of, that's fine. Even like in the art where they don't do any calculation. So for that one there, you can give like 20 minutes to 20 objective questions, depending on the nature of the question. But for our case, there is not. So you can't use 1 minute for a question like that. At least 30 to 20 is fair enough. And even if the questions are involving, then at least you will need more time. Okay, so I think that is the only way. I cannot do it, because if I say no, or we do this at the end, they are setting the questions and after they give you like the same 20 minutes, it'll be like I've deceived you or I've lied to you. So the best way is that we'll find maybe one evening, maybe just like some 30 minutes, then we'll all meet online. Then we tell them our problems and then see how they will address them.
And Mr. Vestal could need respond to the more high power. Say, Mona, which actually I didn't know when I said the question. Yeah, so, oh, my crowd.
Well, that's how good is for them.
At least, almost set the question is on my and I'm a boy. The normal circumstance.
Yeah, for the mainstream, the regular, that's how it is. So once you teach the course, you set the questions for the student, but for code is you will teach, then the coordinator will set. So that's how they do their things. So that I like how WAIC does their things. So they're like WAIC, you have teachers who are teaching the students, and then they have examiners who will set the questions for them. Yeah, so I've heard what you said, and then that is the only way I can also, suggest to you. So maybe we'll find time, then meet them. As you said, this your final service, and maybe.
Yeah, your family and I'm here. Third class beddos.
It will not.
Your family, my nah. Oh, I know it.
But Ibrahim.
Yes.
I would say last block, no, I think when we raised this concern, some of the lecturers helped us with some tutorial questions. I don't know if you intercepted some of them, like thermal optics. So I think as much as we have this genuine concern, they were also well addressed, and then they responded to us also in a very, I think, fair manner. Because thermal like this, though unfortunately I couldn't solve some of these what's the name, tutorial questions, but then I realized after the paper that some of them came. So I think we are also looking at some of these things.
You are right. You're right.
Any other thing?
Sir Festus, please, I heard you said tomorrow we'll be meeting and then we'll continue the next unit. So I wanted to. Does that mean we are?
Forgotten? It's the other course. Because I know that tomorrow we have a class, but
okay,
but that'll be next week.
All right.
3 weeks to go. Sir Festus, 1 week off. I can't tell you.
So why you need off? So
Don't
worry. At least the other thing is just squeeze some time and then go over, look at the equations. Mhm. Actually, like physics is not for the weak. The course itself is not. And then the time. The problem is the time. You don't have ample time to learn. That's why. And so just let's say probably after we met like this, and you don't have time. So you don't have time to go over. Then we learn the other unit. So you see that like you have so many things that you've not learned, and then just like so 4 weeks to exams. So let's see. At least it's always the beginning that is always matters. The end is always like easy. So probably this semester will be like the easiest semester for you. Maybe you are about
Amen.
Please, we will treat you people like babies. All right. If there is nothing more to discuss, then
Let's call it a day.
Yeah. Then, God willing, we will meet tomorrow. I don't even know the time we are meeting.
It's morning 7. God willing.
7. Oh, okay. Yeah. Then.
God bless you, sir.
Amen. Bless you more.
God bless you. God bless you. God be with you.
Yeah. Bye.